Speed, strength, stealth and power. The submarine is a mean machine. It takes man into a hostile world. Today's submarines are technological masterpieces. This is a machine designed like no other.
We don't build prototypes. The submarine has to perform first time it goes to sea.
For 200 years, it's been a process of trial and error in the search for perfection, evolving to fight two different but deadly foes. The massive force of the ocean, and an enemy scanning the depths for the telltale signs.
Once we give ourselves away, that's the end of the game. You may as well go home.
Have we built the ultimate submarine? This is HMS Trafalgar, one of the Royal Navy's ultra-quiet, super-fast submarines. Its weaponry can take out targets 1,000 miles away. Its nuclear-powered propulsion delivers an astonishing 15,000 horsepower. This is where we are today, but how have we got here? Submarine design has been evolving for centuries. The dream of travelling underwater existed long before it became a reality.
Man had fiddled around with the concept of the submarine for hundreds of years.
All kinds of prototypes have been built, but they all hit the same stumbling block: how to devise an effective means of propulsion. In 1897, an Irish-American inventor had a flash of inspiration.
And then along comes a man called John Philip Holland, who had the notion of marrying the internal combustion engine with the battery. And therein really lies his genius.
Here's Holland 1, a product of that genius. Built in 1901, it used a petrol engine to drive it on the surface. But this engine did a second job. It charged an electric battery, which in turn would propel the submarine underwater. Holland's early designs had been driven by a desire to build a weapon to attack the hated Royal Navy. But his genius was such that even the British government put aside their reservations that these were ungentlemanly machines. Holland 1 was the first ever Royal Navy submarine. But its great strength, its petrol engine, was also its Achilles heel.
Well, this is a little trough full of petrol.
Very volatile, gives off lots of fumes which affected people on board the submarines, catches fire very easily. A lot of explosions and fires on the early submarines.
A safer, more stable fuel was needed. The obvious candidate was diesel.
And this is a trough of diesel.
The important thing is it gives off much less vapour, it's much less volatile, has a higher flash point.
It takes the concentrated flame of an industrial blowtorch to set it alight. First used by a French submarine in 1903, by World War I, diesel was the fuel of choice in every Navy's submarine fleet. But it was the German Navy that would really exploit the diesel-electric engine. By World War II, their U-boats had evolved into highly reliable, deadly submarines. They wrought havoc in the Battle of the Atlantic. But even the U-boat was still reliant on electric batteries for underwater propulsion.
The big limitation that a diesel submarine had was that it had to charge its batteries. It was totally dependent, at the end of the day, when dived, on its batteries.
And to recharge those batteries, the submarine had to come back to the surface every 24 hours. The diesel engine that charged them needed to take in air.
The time that a diesel submarine was most vulnerable was when it was recharging its batteries.
Underwater, the submarine was almost invincible. On the surface, it could be a sitting duck. By the end of World War II, the days of submarine supremacy seemed numbered. Then came a new kind of fuel, nuclear power. With it, a submarine need never surface again. The American submarine Nautilus was the first to use nuclear propulsion.
In 1955, when USS Nautilus made the famous signal underway on nuclear power, it was announcing that the world has seen its first true submarine.
Nautilus marked a step change in the way a submarine could be used.
With the arrival of nuclear submarines, you've got a submarine that was effectively a true submarine. It really was independent of the air, of the atmosphere, and that gave it a tremendous capability.
This is one of Britain's first nuclear submarines, HMS Courageous. Built in the late 1960s, its energy source was equivalent to the output of a power station. Rupert Best was one of the Royal Navy's nuclear pioneers. He was a key member of Courageous's construction team and went on to captain her during the Falklands War.
The thing that really struck one in seeing her launch and then joining her was how very much bigger and a much more substantial vessel she was than anything I'd served in before. And that size and, of course, the capability of nuclear power gave her qualities which a conventional submarine would never have had and never could have.
Submarine propulsion had been transformed. With unlimited power, the submarine could go anywhere in the world, and for the first time, it was faster than a surface ship. Now, the ultimate submarine was becoming a reality. Of all the threats the submarine must face, there is none more dangerous than the sea itself.
They live in a naturally dangerous environment. The sea it's just waiting to get in, so you've got to keep her out.
A submarine's hull has to withstand the enormous forces of water pressure. The deeper it goes, the greater the strain. At 200 meters depth, there's a force of 150 kilograms pressing in on every square centimetre of the hull. At 500 meters, this is more than doubled. Submarine designers had always built their hulls to a safe theoretical working depth. But what would happen if a submarine went beyond this limit? In 1945, they decided to find out.
At the end of World War II, the Royal Navy took a number of redundant S-class hulls and literally put them into deep water to wait for the moment that they crushed.
These dramatic tests gave a startling insight into the limits of the pressure hull.
You had an absolute percussion. It was like a gun going off. Literally went from creaking pressure to snap. The whole thing imploded. In one sense, from a submarine point of view, that's quite reassuring. At least it'd be quick.
Paul Morehouse builds submarines to order. The thickness of the steel he uses depends on how deep the submarine needs to go. The inner core of the submarine, the pressure hull, has to be able to withstand it.
This pressure hull here is designed to dive to 300 meters, and it's made of steel, high-grade steel, which is 16 millimeters thick. And it needs to be all of that because the pressure outside is 30 times as high as it is normal atmospheric pressure.
But weight limits how thick the steel can be.
Sometimes people think that you have to have it heavy to make it sink, but in fact we have to keep things light because we want to go as deep as we can.
The solution to the strength-weight equation is to make the pressure hull round. Roundness distributes the water pressure evenly. But the masterstroke came in the early 19th century with a deceptively minor addition: metal ribs.
If we didn't have these ribs, then it would be a little bit like a Coke can. It's very easy just to squash a Coke can because it can't resist outside pressure. You can very easily put a dent in it. And if you didn't have any ribs, it would be the same with a submarine hull. It'd be easy to put a dent in. And as soon as it started to go, then it would collapse all the way.
So just how much difference do these ribs make? This is one of the largest pressure chambers in the world. Fully flooded, it can simulate sea depth of 1,000 meters, beyond the pressure that most Navy submarines can withstand. Two steel pressure hull models of identical thicknesses are about to undergo a searching examination. One has ribs. Both will be tested to their limit. At 100 metres depth, both models are intact. At 200, still no sign of implosion. Then, at 300 metres, the ribless model collapses. The ribbed vessel is yet to show any sign of stress. Then finally, at 400 metres, a spectacular double collapse. The test models were identical, but the addition of 3 small ribs enabled one to go 100 metres deeper before imploding. So the ribbed cylinder gives the pressure hull the strength it needs to keep out the phenomenal force of the sea. But a submarine needs more than just strength and speed. Control is vital. It has to be able to manoeuvre underwater. To do that, it needs wings. Submarines are instruments of war. They rely on stealth and surprise. They need to be underwater for these qualities to shine.
To make a submarine go underwater and to control its depth is a little bit more complicated than the popular assumption.
To submerge, manoeuvre underwater and surface, a submarine needs control. Early submarine designers grappled with the problem of how to control their submarines. To submerge was easy enough, but to return to the surface, another matter. Whatever the shape or size of the submarine, the big problem was getting the weight right, because this determined the buoyancy. Even today, this is an issue.
The weight of the submarine is absolutely critical. We weigh all the equipment that goes on board. We even weigh things like pipe clips. We know how heavy electrical cable is by the meter. So we know how much weight we're putting on the submarine. And there is a whole department which concentrates solely on weight control, because that will define its buoyancy, its stability, and all these other naval architecture parameters.
By the late 19th century, submarine designers had learnt that by attaching ballast tanks to the hull and letting water into them, they could make the submarine submerge. For the diver, his ballast tank is the jug. But to return to the surface, the water had to be pumped out. This was very difficult with manually operated ballast tanks. The breakthrough came in 1888, when a French submarine used compressed air for the first time to force the water out. This meant that at last, a submarine could determine precisely when and how quickly it returned to the surface. Buoyancy control had been cracked with compressed air, but there was still the problem of how to manoeuvre the submarine effectively underwater. Within 5 years, the French had again provided the answer. Give a submarine wings.
A lot of people don't realise that a submarine essentially flies on its hydroplanes like an aeroplane.
The only way it can move in the water, up or down, or through the water, is by being propelled, and by the diving surfaces, the hydroplanes, forward and aft, which tilt to drive you down, tilt up to drive you up.
The French Navy added small horizontal wings to the front of an experimental submarine. They behaved in a similar way to a fish's fins. The submarine's manoeuvrability was dramatically improved by the addition of these hydroplanes. And all this 10 years before the Wright brothers took off. From now on, submarines could fly. So underwater control has been revolutionised. Though very vulnerable if hit, once dived, the submarine is extremely difficult to find. Yet one of the tools it uses to hide once threatened its very existence. At the end of World War I, submarines ruled the ocean, but then a new invention changed the whole game. Sonar.
Sonar was the underwater equivalent of a radar system, and it performs in very much the same, except radar uses radio waves and sonar uses sound waves.
and sound waves travel 4 times faster and further in water than in air. With the invention of sonar, submarines could be detected by surface ships. But submarine fleets acted swiftly. By 1939, they had their own sonar equipment, and they too used it to find their targets.
Active sonar is when we actually transmit, and we transmit a pulse of energy that will go out through the water as a ping. We've probably all heard it on films. It will hit, be it another submarine, and bounce back, which will give us a range.
As the Battle of the Atlantic raged, the pressure was on submarine designers to invent a device that would defeat sonar. It was German engineers who made the breakthrough with an ingenious cloaking device, rubber tiles. But these new cloaked U-boats became operational too late to affect the outcome of World War II.
Basically, the tiles are a rubber overcoat, and if you're transmitted at by an active sonar, the tiles will, first of all, diffuse and soak up the energy of the transmission made at you.
But even the latest rubber tiles can't make a submarine completely undetectable. By the 1950s, the whole emphasis had switched to making submarines as silent as possible. But that's no easy business.
We are in, for want of a better word, a tin can. Now, anything that rattles or shakes in that tin can is totally magnified, amplified, and will emit a sound out through the pressure hull so that be it other enemy submarines can pick us up.
You build quietness into a submarine with extreme difficulty because the loudest noise that you cure, great, I've cured the loudest noise, I now have a new loudest noise. So it is always a battle to cure the next loudest noise.
This is HMS Onyx, one of the Royal Navy's Oberon class of submarines. Decommissioned now, but when built in 1967, there was nothing else like it.
It was a very quiet diesel-electric submarine, and in electric mode was very, very difficult to detect.
Oberon submarines closely monitored their own noise. They put shock absorbers on machinery to stop vibrations going through the hull and out into the sea. Today, this technique has been taken to a whole new level. This motor is sitting on a metal plate. Sensors have been connected to measure the sound waves transmitting through the metal plate into the water. The noise generated is displayed on these screens. But when a piece of foam rubber is inserted between the motor and metal plate, a dramatic reduction can be seen. In submarine construction, this is known as rafting. Keith Gain served as a sonar operator on Royal Navy submarines. He followed a strict Cold War regime of silence as they sneaked up on Soviet ships.
We would shut down all unnecessary machinery, i.e. fans, anything that's going to make a noise.
Keith used listening devices called hydrophones to eavesdrop on the Russians. Picking up sound in the water like this is called passive sonar.
A passive sonar is where you just want to listen to the information that's in the water around you. We have a ball hydrophone here, which is commonly used in sonar systems. If this was dipped into the sea, it would be very much like a microphone, which you could listen to all the underwater sounds.
Keith and his fellow sonar operators could almost hear a pin drop.
Say if someone in the engine room, for instance, and was doing a repair and he had a spanner and he dropped that spanner onto the deck plates, you would get a crash which would be like banging a drum, basically. And you would hear that for 50, 60 miles away. Contact bearing 220, classified warship.
With passive sonar, Keith's submarine could get a contact and sneak up on an unsuspecting enemy.
We'd have a listen to what was going on, what was being said over the intercoms and communications. We might pop up the periscope, take a few sneaky snapshots to try and gather more intelligence.
This was a very dangerous game. On one occasion, noise from a chip propeller nearly gave Keith's submarine away.
The whole back end of the submarine was shaking like a dog shaking its tail and resonating a very loud noise.
Keith and his crew were lucky. On another day, this could have proved fatal. Much depended on the sonar operators. They relied on their own skill to distinguish the manifold noises of the sea.
It's fascinating, the sea noises. You have the snapper fish, like that sort of noise. You have the wailing noise of the whale, which is like cries in the ocean. And when you're under the ice, and say at the North Pole as submarines go up there, you hear the ice crunching and creaking and moaning. It's very eerie but very fascinating noise.
It's very difficult to discriminate sometimes between what might sound like a submarine target and is actually a seal or a groper fish or a whale.
In the late 1990s, sophisticated computer sonar analysis was introduced on all Royal Navy submarines. It classifies different underwater noises. It helps the sonar operator make sense of the sounds he hears, each with its own acoustic signature.
You could get, say, a fishing vessel, and it's very fast revving, it's got a high-speed diesel engine in.
Of a merchant ship,
on a warship, it might be. Chick, 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 chick.
So the modern submarine is a highly evolved weapon of detection. It uses ultra-sensitive ears for both defence and attack. Submarines in the 21st century are very fast, virtually silent, can go anywhere they like, and need never surface throughout an entire patrol. But these are still not yet perfect machines. The loss of 4 Russian submarines since 1970 highlight the dangers of nuclear power. Even the nuclear reactor may eventually become obsolete.
One day, somebody will have a breakthrough on battery technology. That, combined with fuel cell technology, may very well write the end of nuclear-powered submarines.
In the never-ending search to build the ultimate submarine, others foresee a different future. Not so much changes in technology, but a rethinking of the whole role of submarines.
The submarine of the future will be a mother ship fitted with lots of remotely operated babies. And these babies will have a variety of roles. There'll be mine hunters, there'll be intelligence gatherers, there'll be communications surveyors. So you're going to end up with a highly flexible, multi-role, invulnerable sea control machine. And it's a very exciting prospect.
Agile athletic, the helicopter defies physics.
Like the Bumblebee, which on paper shouldn't fly, it somehow does.
This is the only machine perfected to take off vertically and hover.
It's the hover that makes the helicopter different.
It can get to places no other machine could dare.
We train for the worst case scenario, and hopefully the worst case scenario doesn't come up very often.
From search and rescue to attack, technology is pushing the helicopter to perfection. To maintain this unique position, it must constantly reinvent itself, and engineers are taking its design even further. Experimenting with new technology, this is the challenge they face as they strive to build the ultimate. This is the EH-101, a state-of-the-art helicopter. It embodies the quantum leaps made in helicopter technology over the last 70 years. It's down to the test pilot to judge the machine and identify problems no one anticipates.
The role of the test pilot is really, he is the link between the engineers, the man who's designed the aircraft, the men who built the aircraft, and what the aircraft actually achieves. So he is the vital link between the airplane itself and the man who imagined it on the ground.
With high-tech avionics, the machine can almost fly itself.
now turn on the electrics. We're just about ready now to start the rotors, and obviously helicopters don't have ejection seats, so perhaps that's what made most helicopter pilots doubly cautious, check everything over twice.
From the rotor to the engine, the helicopter is intricately designed. And from the avionics to the materials, this complex machine performs incredible feats. It's the rotor that makes the helicopter unique. As the blades rotate, the air passes over them, allowing it to take off and fly.
The helicopter flies by rotating its wings through the air. The rotor blades are exactly the same as a fixed-wing aircraft's wings. The big difference being is that instead of the aircraft being dragged forward by the engines to give you the lift over the wings, we actually rotate the wings to give the speed through the air that gives us the lift.
It took 30 years of failed attempts before the rotor was finally perfected. And a few pioneers ensured that the helicopter would be born. The first major step was in 1923, when a young Spanish pilot, Juan de la Cierva, had a major breakthrough while designing the autogyro. Cierva worked out that rotor blades needed two crucial hinges in order to fly. The founder of the largest helicopter museum in the world knows without this eureka moment, we wouldn't have the helicopter.
Juan de la Cierva was able to invent the flapping hinge and the lead lag hinge. Now those were two hinges which were fundamental in making the autogyro work, because everybody prior to that had problems with the aircraft effectively trying to fall over, or there being too much stress in the system which caused it to fail.
For the first 20 years of its existence, the helicopter was developed by a handful of enthusiasts, aristocrats and eccentrics. But not for long. 1950, the outbreak of the Korean War. For the first time in its short life, the helicopter was about to prove itself.
The Korean War, the major issue there was getting the injured out and back to the field hospitals as quickly as possible. And it was quickly shown that the helicopter in that situation was, a lifesaver. It certainly started to demonstrate to the army generals that the helicopter wasn't just a toy, that you could actually do something useful with it.
From Korea to the Cold War, the military now took possession of the helicopter. But they wanted it to do more, to go faster and to carry more weight. And if this was to happen, it was the rotor system that needed to change.
One of the problems with some of the old-fashioned rotor blades is that they were in essence like a plank, slightly aerodynamic plank, but nevertheless a plank.
In 1972, a team of young British scientists set about solving this problem. Peter Wilby and Jeff Byam were part of that team, pushing the technology to its limit. But they faced a classic conundrum that affects every helicopter in forward flight. As the air passes over the rotating blades, it speeds half the rotor up and slows the other half down.
This comes back to what we call the advancing blade problem. And in forward flight with a helicopter, you have the advancing blade here and the retreating blade here. And if I'm going in forward flight, then this blade tip is traveling much faster than the retreating blade tip. So you get two sets of problems. This blade is going slowly at high angle of incidence. This blade is going fast at low angle of incidence.
The team knew that the only way to solve this problem was to drastically change the shape of the blade.
In the early 1970s, blades were very, very simple shapes. They were rectangular and they had almost the same cross-sectional geometry all the way along their length. And we knew that in order to make them more effective, we had to change the planform at the tip and we had to make the cross-sectional shape vary along its length.
We could see there were potentially big gains, but of course we had to convince everybody else that there were big gains.
Not everybody believed us at first. The calculation methods we were using weren't totally trustworthy, so you couldn't just point to an analysis and say, believe it. And so we had to do a lot of experiments. We had to degenerate existing blades. We had to take blades that were already on aircraft and make them a little bit worse in different places to try to see which areas were sensitive. So we found ourselves flying an aircraft and putting sandpaper on the leading edge. And the sandpaper was there to destroy some of the aerodynamic benefits. And then you could map which part of the rotor blade actually had to be attacked first in order to make things better.
It took more than 13 years of tests to change the shape of the tip and develop the right material. The wind tunnel test is the only way engineers can verify calculations before going to full scale. Here, Peter and Jeff return to their prototype to compare traditional blades with the new design.
Drives on.
First of all, they test the rectangular blades. By increasing the speed of the wind tunnel, they measure the limit at which the blades can fly.
Speed increasing.
Their aim is to push the speed, to push the envelope.
The control loads are very high now.
So we could say that this is the edge of the envelope for the rectangular blade.
Very much so, yeah.
And it looks like it's 150 knots.
That's about 172 miles an hour. Next up, the revolutionary swept tip blades. How do they fare?
Better take it gently just to make sure we don't have any problems.
Immediately, it's obvious that the swept tip blades are going faster than 150 knots. In fact, the new blades achieve an extra 20 knots. That's about 23 miles faster in the wind tunnel. Of course, tests can only prove so much, and by 1985, it was time for Peter and Jeff to see if their new blades would work on the real thing.
So you just hope there's nothing unforeseen is going to go wrong. You believe you've covered everything, but you never know.
With bated breath, they nervously watched, but they were powerless, and the new blades were now in the hands of the test pilot.
I suppose within only a few hours we were beginning to realise that yes, it had produced the improvements we were looking for. And a year later, in 1986, almost to the day, we went off and actually took the world speed record.
Flying at 249.09 miles per hour. No helicopter has ever flown faster. Better blades meant a new generation of helicopters that could fly faster and carry more. Whether it's lifting victims out of the sea or transporting equipment across difficult terrain, weight has always been a major enemy of the helicopter designer. But they face a dilemma. They must keep weight down, but they must also use materials strong enough to withstand impact.
One of the things about the helicopter is you want it to be as light as you possibly can, because effectively you've got to lift all that weight vertically before you fly off. And so throughout its life, people have tried to make the helicopter lighter and lighter.
Early helicopters were made of steel. Then, in the 1970s, designers looked at new materials.
They've been able to use fiberglass and composite materials, which have the advantage that structurally they can be stronger.
The benefit is that plastic offers much more than steel.
The whole thing makes the helicopter lighter, pound for pound, and therefore you can carry more.
While helicopter designers managed to make a lighter superstructure, they still have one enemy to overcome in their quest to build the ultimate. And it's not the enemy you might expect.
3, 2, 1.
It's a hazard even the best pilots can't avoid. Bird strike. A bird can hit a helicopter windshield at more than 200 miles an hour. This is what can happen, and it's what glass designers are constantly battling against. Since the early 1970s, helicopter and plane windshields have been laminated to protect the pilot. Laminating a windshield involves layering glass with plastic. But in the event of bird strike, even laminated glass can shatter and splinters can be deadly. Then, in 1986, engineers came up with a new idea. They used chemicals to toughen glass. They tried molten salts and heated them up to 200 degrees centigrade. They submerged the glass in these salts. The result? glass that is 10 times stronger. This stronger glass is layered with plastic to form a composite windshield.
The benefit of using composite material is that when a bird hits the glass plies can break, but it's the plastic layers bonded to the glass that actually stop the penetration of the bird into the aircraft cockpit area.
But every new design needs to pass a test all glass engineers know well: the bird strike test.
It's the ultimate test that the aircraft won't be grounded, won't fall out of the sky, and that the crew won't be killed.
This is a 4-pound pheasant, freshly killed and bound together.
The tonnage we got is 4 pounds, and that's the minimum weight we're allowed.
Okay, well, that's reading 4 pounds exactly.
Okay, that's good.
This 70-foot nitrogen gas gun is highly explosive and can fire a bird at more than 300 miles per hour.
We're setting up for the test for the bird impact test on the windshield on this aircraft, and we're just checking that the windshield doesn't fail when the bird hits it at 270 knots.
That's about 310 miles per hour. Here the target is an aeroplane, but the principle is identical. The windshield must stay intact.
We're going to basically charge the bottles up with nitrogen gas, and when we're ready and we're happy with the pressures, we'll actually fire the button. 3, 2, 1.
Does it look?
Well,
oh, it's excellent. That's a good shot.
Doesn't it?
Yeah.
Hit in the middle. Yes.
All plies intact by the looks of things?
It does.
Yeah, it looks good, Roger. Good centre shot. It looks like it was good on position. And I can't see any visible damage. And I think we look, when we look inside, there's no bird penetration, no plies broken, so it's an excellent result.
In modern helicopters, composites have completely replaced steel and glass, making the machine lighter, slicker, and more efficient. Weight is not just an issue for the superstructure. It's also a problem for the helicopter's beating heart, the engine. The golden age of the helicopter engine was the 1950s. One thing happened that would change the helicopter forever.
I think one of the most stunning step forwards in helicopter was the change from piston engines to turbine engines, because that really made a huge difference in terms of power that was available, the weight of the engine, the fact you could much more easily accommodate 1, 2 or 3 engines in an aircraft.
Well, here we have a typical radial piston engine from the 40s, early 50s. Big, bulky, heavy, lots of things to go wrong with it. And then in the mid-50s, along came the turboshaft engine, far smaller, much lighter, much, much simpler, and 2, 3 times as much power.
Turboshaft engines were transforming all vehicles, and now it was the helicopter's turn. 1965, US troops arrive in Vietnam. Immediately, the increase in helicopter engine power was obvious.
If you imagine that the average family saloon has about 100 horsepower and a really fast production car like some Lamborghini may have 300 plus horsepower, these engines are producing 3,750 horsepower. So you can see the sort of quantum leaps in performance that have been required over the years to enable us to fly these machines.
The helicopter is a complex machine, but it has a unique trick up its sleeve. If the engine does fail, it's possible for the pilot to land safely, so long as he practices.
The classic question is what happens when the engine stops. They have this vision of it plummeting out of the sky, not realising that every pilot is taught how to auto-rotate, which is basically to turn the helicopter into a sycamore seed.
An auto-rotative landing is a controlled descent, whereby the rotors allow the helicopter to freewheel to the ground.
If you can imagine a sycamore seed, it has a small weight on one end and a wing almost, like a rotor blade.
In this practice landing, the pilot is going to temporarily disengage the engine from the rotor.
Captain to crew, stand by for power failure. 3, 2, 1, go.
We don't come down exactly like a sycamore seed in that we don't turn round and round and round.
Watching the speed coming back, we're in auto rotation.
Because of our balancing systems, and on a Chinook here we have 2 sets of rotor blades.
Quick reactions are essential, and the pilot must neutralise the rotor so it can spin freely.
Engines now not driving the rotors. Descent established. Best range speed, 80 knots.
Like a sycamore seed, the wing rotates round in the airflow and it cushions our impact at the bottom.
Looking out for the landing area. Good speed. Descending. Checking the rad alt. On 100 feet to go, flaring. Brace and brace, brace.
At the last moment in this test, the pilot re-engages the engine with the rotor, pulls the nose up to kill speed, and lands safely.
On the ground.
Strides in design have made today's helicopter engine both light and astonishingly powerful. This unique bird can land without the engine, but the weakest link is still the pilot. South Korea 2001. For some unknown reason, the pilot continues to descend, with tragic consequences.
The most common cause of helicopter accidents is still pilot error.
The intensity of the pilot's workload means a lapse in concentration can be fatal. But in the 1990s, electronic engineers began to deal with this problem. With the use of computers, they are taking the pressure off the pilot. The helicopter has one Achilles heel. It's always been exhausting to fly. But the digital revolution that changed the world in the 1990s was about to work wonders on the helicopter.
So I turn the fuel on up here, this computer-controlled engine. So all I do is turn this knob here from off to ground idle.
The digital control of engines has certainly made life a great deal easier for the pilot because he doesn't have to manage the engine in the same way that he used to have to do. It was very much a balancing act in the early days with the relationship between the engine and the rotor because, of course, every time you changed the rotor, you had to change the speed of the engine, and it wasn't automatic. You had to accommodate that yourself as well. With modern engines, with digital control, you set the engines up, they look after themselves, and they provide the power when you want it.
Computers have also transformed the helicopter's guidance in what engineers term avionics. Gone are the mechanical displays. Everything is now electronic, from navigation to night vision. A staggering 1/3 of the cost of the modern helicopter is spent on avionics.
In the early days, and indeed still with some of the simple helicopters today, you're flying manually. So you're still using all your senses to control and fly the helicopter. If you could imagine a ship in distress far out at sea, and a helicopter which has to sort of navigate through a range of mountains to get to it, all that can be done virtually automatically now.
This means that the helicopter can now fly in unforgiving conditions.
We train for the worst case scenario, and hopefully the worst case scenario doesn't come up very often. But when it does, you have to rely almost 100% on the success of the avionics to complete your mission.
December the 18th, 1996. Jamie and his team were called out to a medical emergency on an Irish ferry.
The main avionic which helped us to start with is obviously the radar, to locate the vessel and then to allow us to close and make an automatic transition down to within a quarter of a mile.
20 years ago, without any computer assistance, this manoeuvre would have been high risk, raising the stakes in pilot error. But with avionics, Jamie's pilot could do the job safely.
What the aircraft will do is, flying at 200 feet, all you have to do is press a button and the aircraft will then automatically start to descend and to slow itself. It will then come down to a 50-foot hover without the pilots touching the controls.
With the helicopter now in position, Jamie was able to be winched down to the ferry and recover the victim back to the helicopter.
And the aircraft from its hover will then start to move forward and start to climb away. At the stage it will get up to 200 feet and 90 knots, and the autopilot will click off, and at that stage the pilots can take over and fly us back on a route towards the hospital.
Without avionics, search and rescue would be difficult. Night flying limited. Saving lives treacherous. Advances in technology mean the helicopter can fly day, night, all weather. Operating stealthily, it can almost fly itself. In 70 years, the helicopter has changed beyond recognition, and it'll change again. But in pursuit of making the helicopter faster, there's a danger that designers could undermine its uniqueness.
Each of those steps to go further and faster actually damages the helicopter's ability to hover quite so well. And yet really it's the hover capability which is the essence of the helicopter.
To fly faster, helicopter blades must be broader, but this makes them heavier and less able to hover and to lift.
I think to go faster and yet still be able to hover, you have to add some extra device to a helicopter.
Designers think they may have the answer: the tilt-rotor helicopter.
I think the future is a helicopter that can turn its rotors to become propellers, and therefore it can go much faster and go longer distances than the conventional helicopter.
Helicopter engineers are still striving to build the ultimate. The tilt-rotor is already in production. It should be in service with the US Marine Corps by 2006. Civilian tilt-rotor helicopters will follow soon after. Japan. This is the Akashi Kaiko Bridge. With a main span of almost 2 kilometers, it's the longest suspension bridge in the world.
It's like you get a whole mile of the M25 complete with a traffic jam of trucks. You pick it up 100 feet in the air, the roadway as well, and you hold it from cliff to cliff. They're just huge feats of engineering.
Uniting people across the widest rivers and the deepest ravines. In the world of bridges, the suspension is king.
I just built the bridge and move a tiny bit then. Right. That's interesting.
Yeah, it's moved for you.
For 200 years, bridge builders have been trying to perfect this complex structure. They've battled to overcome the elements and learnt some painful lessons, often the hard way.
You know, it's a horrible, horrible thing. It's making the hairs on the back of my neck stand up as I think about it, because you just don't want to go there.
To design longer and longer suspension bridges in ever more difficult locations, this is the challenge designers face as they strive to build the ultimate. The suspension bridge is the only structure known to man that can span more than a mile. Defying gravity, it makes light of difficult crossings. From the deck and the towers, the magic of this bridge is how the load is distributed up to the cables and into the anchorage. This bridge must deal with many forces: its own weight, the weather, and the weight of traffic. Every year, 40 million vehicles cross the Golden Gate Suspension Bridge in San Francisco. The Menai Strait Suspension Bridge in North Wales is one of the oldest in the world. Most of its contemporaries collapsed due to bad design and a lack of understanding of how this bridge really works. Chris Wise designed the London Millennium Bridge and is a professor of civil engineering design. Like all engineers, he's constantly second-guessing the possible threats to the suspension bridge.
When we work through a bridge design, we take all the obvious things, every single natural phenomenon that we can imagine, so gravity, wind, hurricanes, and then we also have to think about what happens if a terrorist attacks a bridge, because a real major bridge like this is a fantastic target for terrorists. You imagine somebody going for the Golden Gate Bridge or the Sydney Harbour Bridge. So we have to consider when we're designing these things, what would happen if somebody cut one of the cables, for example. And the Millennium Bridge is designed so that a certain number of cables, and I can't tell you how many, can be taken out by a terrorist attack and the bridge will still survive.
With nothing supporting it from underneath, the length of a suspension bridge is calculated by the span between the two towers. The towers in a suspension bridge are like the poles in a washing line. The main cable hangs between them.
Well, the towers they're probably the most important thing. If the towers fail, the whole bridge falls down.
But just how the towers work is a surprise.
They have similar properties to a tree. If you imagine a tree in a strong wind, it doesn't try and stand there and resist the wind by just going like that. It actually allows it gives, and in giving, it allows the wind to dissipate its energy.
It took many years for engineers to learn the basic principles. Without a few key pioneers, we wouldn't have the suspension bridge we see today. The Clifton Suspension Bridge is a masterpiece of engineering, designed by 23-year-old Isambard Kingdom Brunel in 1829. So perfect was his design that it remains structurally unchanged to this day. Sadly, Brunel died 5 years before it was finished. The masonry towers are 26 metres high, but it soon became clear that masonry had limitations. Longer bridges needed taller towers. Masonry towers could never be tall enough. And this wasn't the only problem with it. Masonry is a brittle material. If shaken, it collapses like a deck of cards. This is the aftermath of the San Francisco earthquake of 1906. 25,000 buildings were destroyed. Nowhere were the limitations of masonry more obvious. Then came steel, and with it the chance to build higher towers and so longer bridges, like the Golden Gate. And steel had another advantage in earthquake zones like San Francisco. It was ductile.
Ductile means that it doesn't snap easy. It's the opposite of being brittle. So with ductile, there's two reasons you want it to be ductile. One is because it gives you a warning that it's about to go, that when it first starts to really bend, you can see that something's happening. And the other one is, in a dynamic case, it absorbs energy because you can go backwards and forwards. Whereas with brittle materials, it just goes bang and everything falls to the ground. You have no warning, there's no energy absorption, everything just breaks all at once.
When the Golden Gate Bridge opened in 1937, it became the longest bridge in the world. With towers of almost 230 metres, almost 10 times taller than the Clifton Suspension Bridge, the Golden Gate became a world icon. For 50 years, steel ruled, but it came at a high price. So in the 1970s, designers came up with a solution to unite the flexibility of steel with the convenience of concrete. The way forward was steel-reinforced concrete. Fulfilling a personal ambition, Chris Wise goes to see the inner workings of the first bridge in the world to be built with concrete towers. The Humber Bridge in East Yorkshire.
No, it's surprisingly well behaved. I mean, I was expecting to see it, to almost see it moving. Because when you look at it from ground level,
yeah,
it looks so slender. You know, you see this fantastic thing just going across the water, and it's you know, you almost expect it to be moving around. It'd be a bit more lively.
Opened in 1981, the Humber Bridge is today the fourth longest in the world.
How fast the wind actually going?
About 10 metres per second.
10 metres, it's about 25 miles an hour, roughly.
Going up to...
Actually, I just felt the bridge, I felt it move a tiny bit then.
Right.
That's interesting.
The Earth's moved for you.
Yeah.
With reinforced concrete towers, suspension bridges can now be built at a speed that would have astonished the early pioneers. But the real ingenuity of the suspension bridge is the suspension system, made up of the main cable and hangers. Everything depends on the cable, but it's also the bridge's Achilles heel. When Brunel built the Clifton Suspension Bridge, he used 4,200 second-hand chains that had been on the Hungerford Bridge in London.
Historically, they used to use chains for suspension bridges, and they made the cables out of wrought iron chains made out of loads and loads of individual pieces, and it was very complicated. It took ages.
Heavy chains meant that much of the bridge's strength is taken up in carrying its own weight, so span and traffic is limited. Then, towards the end of the 1800s, one man working in America was about to change that. This is the Cincinnati Roebling Bridge, named after the man who designed it, John Roebling. A tortured genius, he was obsessed with pioneering a new design in bridges. The Cincinnati Bridge was just a dry run for a bridge that would make Roebling an international name. In 1883, the Brooklyn Bridge in New York was about to become the world champion. On its completion, its towers would stand at 84.3 metres, the tallest structures in Manhattan at that time.
What amazes me the most about the Brooklyn Bridge is its complexity and the time period that it was built in. You have to remember, this bridge was started in 1869, just a couple years after the Civil War. There was no electricity, there was no machinery, no gas combustion engines. This bridge was built just with the use of steam engines and was literally built by hand.
But Roebling's true genius was in how he made the main cable. He didn't use wrought iron chains. Instead, he used the most modern new material, steel. And to make the bridge lighter, he spun the steel back and forth across the river.
Hey, the main cable is the lifeline of the bridge, and this cable is made up of thousands of bridge wires, which are about the diameter of a pencil. And there's literally thousands of these wires within the main cable itself.
This move to spun cables in New York in the 1860s changed the face of the suspension bridge forever. 100 years later, when Doug Strachan worked on the construction of the Humber Bridge, cable spinning had become an art.
We take a spinning wheel across the river, and when the spinning wheel gets to the anchorage, the loop is taken over and the wheel comes back empty. They then take another loop and the wheel starts off again at the anchorage, taking the second loop of wire across the bridge, and in that way you build up the cable of the bridge.
The cable is then anchored with a huge amount of concrete into the ground.
How many strands of wire are there in this fantastic contraption?
Well, the whole shebang's 15,000 wires, but the reality is there's only 37 wires, and they all, each of them crosses the river 400 times.
They look like they last forever, these things.
Well, they're supposed to have a life of 120 years. This is, if anything, the Achilles heel of a suspension bridge. Very, very difficult to replace. And somebody once said that trying to replace the cables on a suspension bridge is like going to the dentist, and he says, well, your teeth are all right, but your gums will have to come out.
The huge leaps forward in the technology of the suspension system have enabled designers to increase span, connecting more and more people over greater distances. But once the cables were finally perfected, it was clear to engineers around the world they had a lot of work to do on the deck. By the mid-20th century, the suspension bridge had come into its own. But in November 1940, something happened that would change these bridges forever. The Tacoma Narrows Bridge in Washington State opened in July 1940 and hit instant fame. Christened Galloping Gertie, this newly opened bridge began to oscillate uncontrollably.
It's making the hairs on the back of my neck stand up as I think about it, because you just don't want to go there. You know, it's a horrible, horrible thing.
On the 7th of November 1940, Galloping Gertie collapsed. For designers, nothing would ever be the same again. The collapse of the Tacoma Narrows was a wake-up call for suspension bridge designers. In pursuit of slenderness, they'd underestimated the power of wind. The mystery lay in the fact that Tacoma was designed to withstand 120-mile-an-hour winds. Yet the wind speed on the 7th of November 1940 was only 40 miles per hour. The key to unlock this mystery would be found in a phenomenon called natural frequency.
Natural frequency is it would be something that's very familiar to anybody who likes music. It's the note that something makes. And if you pluck a guitar string or a violin string, you hear a note which has a particular frequency. And bridges are no different.
We've got three structures here. They've each got a different natural frequency. The natural frequency is the frequency it wants to vibrate at if you just give it a twang. And so we've got a really slow natural frequency here, got a really fast one, and we've got one in the middle.
In this test, the Tacoma Narrow's natural frequency is most similar to the slow one. When winds hit a bridge, they create mini whirlwinds, called vortices. The problems start when these vortices have the same natural frequency as the bridge. This is called resonance.
If I now start to shape this support for these three bridges, if I do it really slowly, just give it a little motion, at the natural frequency of my big slow one, you can see that the big slow one really starts to respond, and we get massive amplification. And the other two are hardly doing anything. If I do it at intermediate sort of speed, the middle one goes wild and the other two stop. And if I go really fast, just the little one goes wild and the other two stop.
On that morning, with vortices created at the natural frequency of Galloping Gertie, it was only a matter of time before resonance caused the bridge's collapse. Tacoma terrified bridge engineers. Suddenly, wind was the enemy. They went back to the drawing board and discovered that the way to combat resonance was to bolt extra beams underneath the deck, called a stiffening truss. At vast expense, bridges around the world, including the Golden Gate, were retrofitted. It seemed the stiffening truss was the only way forward. That was until the late 1950s, when a young British designer came up with a new idea. And after countless awards, more than 40 years later, Bill Brown still plays down his role.
I think I was probably at the right place at the right time, in fact.
The magic of Bill's idea was to work with the wind rather than against it.
I didn't know that it would work aerodynamically. I knew it would work structurally, but not whether the aerodynamics would work.
Bill came up with the idea of reshaping the deck of the suspension bridge to make it aerodynamic. The wind is deflected around it, and the deck flies in the wind. Bill had just finished the 4th road bridge and had won the commission to build a crossing over the River Severn. This would be the first bridge in the world to have this new deck. But first, he had to test it. 40 years later, Bill demonstrates what his wind tunnel tests showed. First up, he tests the Tacoma deck.
You can see the Tacoma Narrows section is twisting quite violently.
At just 40 miles per hour, the Tacoma deck cannot withstand the wind.
I think that's enough, otherwise we'll damage the models. So we take this and we'll now put in the model of the Severn Bridge, which is a longer span of different cross-section, and we'll run it at a much higher wind speed.
The effects of the wind on the aerodynamic deck are plain to see.
We now have mounted the Severn cross-section, and we're running this now at 150 miles an hour. And as you can see, it is absolutely stable. This is because we have an aerodynamic section, the wind is flowing above and below it, streamlined, and the forces are low.
The Severn Suspension Bridge was opened in 1966 and would lead the way in modern bridges.
The magic is that it is streamlined and therefore the wind forces are low and there are very few vortices. So generally speaking, we don't need to add structural resistance to overcome the wind forces.
After the success of the Severn, bridges around the world were built with aerodynamic decks, starting with the Humber.
This is Bill Brown's aerodynamic deck, is it?
Absolutely right. It's quite flat over the top and then quite low down here, so you get the right aerodynamic effect.
So the wind goes over the top?
Yeah, the wind route over the top is shorter than the route underneath, so it's an upside-down aircraft wing. It's got negative lift.
Resisting wind and earthquakes is a challenge, but there are other forces of nature out to get the suspension bridge. Over the years, engineers thought they understood the effect of people walking on a bridge, but they didn't.
How's you two? Break stop! Boots!
Everybody knows about the Roman army having to break step when they go across bridges. And the reason for that is because they march very regularly. You have lots of people all putting their feet down at the same time. And if you get a bridge which happens to have a frequency which is close to that, the Romans must have found out 2,000 years ago that if they didn't break step, they would actually knock the bridges down.
2,000 years after Roman soldiers marched on London, this issue of footsteps would be a problem for Chris and the team at the grand opening of the Millennium Bridge over the Thames. Opening day, June 2000, and the bridge did what no one expected. It started swaying from side to side. The first Mike Wilford knew about it was when his telephone rang.
I had a phone call from one of my colleagues who was on the bridge asking me whether I'd come down and take a look at it because it was vibrating. And I said, goodness, not bouncing up and down, is it? It shouldn't do that. He said, no, it's going from side to side. And that seemed very strange to me. So I got in the car and came down to take a look at it.
This swaying bridge caught the headlines and became talk of the town.
Obviously, it's the sort of thing you dread. You know, I hate the fact that the bridge didn't work perfectly.
We were a bit embarrassed that the bridge wobbled in a way that wasn't predicted or wasn't expected.
Designers needed to act, and to act quickly. From looking at the bridge, engineers discovered that the swaying was caused by people's footsteps.
There were enough of them that they, strangely to us, all decided to walk at exactly the same speed, and we couldn't understand what the hell was going on.
What people were doing was synchronising their footfall. Not up and down like marching soldiers, but from side to side.
What we found was that when the deck you're walking on moves a little bit side to side, you tend to synchronise your footsteps with that motion and also place your feet further apart to improve your balance. This increases the lateral forces on the system, so the sway gets bigger and bigger.
Just like a child's swing, the bridge created its own positive feedback, and with every sway, it gained momentum. This movement was christened synchronous lateral excitation. Engineers had known about it in theory, but this was the first time they began to really understand it.
It did put the spotlight on lateral excitation, which most suspension bridge designers had never worried about before for people walking. They'd always concentrated just on the vertical. Now we do have to think about the lateral a lot more.
The problem that took time to understand was quick to solve.
It was solved by putting dampers on it. You just put these big, like bicycle pumps full of honey, and they just drain the energy out of it. If the structure moves, these dissipate energy. It's very simple to fix.
This new discovery caused a stir around the world.
Every bridge around the world was checked for this phenomenon of synchronous lateral excitation to make sure that it wouldn't happen on their bridge. And many of them, it turned out, had actually been moving very quietly without anybody really mentioning it, because everyone was too embarrassed about it. But a lot of bridges have been retrofitted with dampers as a result of the problems that the Millennium Bridge had.
With every new bridge built comes a greater understanding of the dynamics of the suspension bridge. Getting a grasp on resonance and aerodynamics means decks are now safer and longer. For the past 200 years, the suspension bridge has evolved to span greater and greater distances. But despite all these advancements, engineers still think it can be improved.
Most people who design bridges want to stay just on the side of danger. You know, they try and be a little bit conservative. And as a result of that, you see an awful lot of bridges that look almost exactly the same all over the world, and many of them are horrible. But sooner or later, somebody has to be adventurous, and bridge designers who do that need to be applauded, because if they didn't have that degree of adventure in them, the technology would never move forward, and we would never have been able to get from one side of the Thames to the other, ever.
40 years after his revolutionary Severn Bridge, Bill Brown is still pushing new frontiers. Today he's designing a bridge that will be more than 1 kilometre longer than any bridge yet standing. And there's a new generation of bridge around the corner. Engineers will soon be harnessing computers to their suspension bridges.
I think that the future of suspension bridges will be actively controlled bridges. And when a hurricane hits them, something will happen, a servo will kick in, and it'll pull the bridge away from the hurricane to make it stand up.
Bridges able to make decisions when faced with unexpected forces means the suspension bridge will unite even more people as they span ever greater distances.
And we have a go for auto sequence start.
At the beginning of the 21st century, a spacecraft heading off into space is such an everyday event that it hardly makes the news.
T-minus 31 seconds.
But the technology that hurls men into space is literally out of this world.
Astronauts are the fastest human beings ever, by a long way.
For 50 years, it's been a great adventure. Fueled by the military and the politicians and shaped by the passion of pioneers, spacecraft are going ever further into space to explore our universe.
3, 2, 1, and we have liftoff.
But it's never been an easy ride.
I would never want to be an astronaut because I know how rockets work.
High-profile tragedies remind us it's still a risky business. To crack the problems of space travel, engineers have tested materials to destruction at speeds beyond imagination. So, at the beginning of the 21st century, are we anywhere near building the ultimate spacecraft? This is the American Space Shuttle Atlantis, the most sophisticated spacecraft in operation today, and the culmination of 50 years of design and development. It's made from 2.5 million parts. The rocket boosters use 10 tons of fuel a second. It can carry a double-decker London bus in its cargo bay. It's a state-of-the-art spacecraft. The shuttle is made up of the orbiter that carries the astronauts, a huge central fuel tank, and 2 rocket boosters.
The problem about getting into space from the Earth is that the Earth has very strong gravity, and this means it's very difficult to get into space. To do that, you need to travel very, very fast indeed. The only real way you can do that is to use a rocket.
There are liquid-fueled and solid-fueled rockets for space travel. What's unique about the shuttle is it's the only manned spacecraft ever to use both kinds of rockets simultaneously. A brilliant, but as it turns out, deadly innovation. But the story of rockets begins in 300 BC. Rockets were first invented by the Chinese. The fuel that propelled them was gunpowder, and for over 2,000 years they were used as a weapon of war. For centuries, man had dreamt of reaching the stars, but it was a Russian mathematician, Konstantin Tsiolkovsky, who first suggested rockets as the way to get there.
Tsiolkovsky worked out this equation, which explains exactly what you need in order to develop a good rocket. And it's very simple, so I think I'll write it down.
The V on the left is the velocity you need to get into space. On the right, the energy that can be generated by a gunpowder-fueled rocket.
Tsiolkovsky would have looked at this equation and realised that there was no way that human beings could build a rocket that would take you into space.
For the equation proved that a rocket big enough to carry enough gunpowder would be too heavy to get off the ground. Tsiolkovsky spotted that a liquid-fueled rocket wouldn't have the same problem, but it would be another 30 years before a group of young German rocket enthusiasts, led by a charismatic 20-year-old called Wernher von Braun, perfected a liquid fuel.
They really saw that as the first step into getting into space. But of course, other people had different ideas.
Liquid fuel rockets were first used not to put man in space, but to drop bombs on London.
Wernher von Braun is one of the great pioneers of spaceflight. At the end of World War II, he and about 150 of his key associates surrendered to the Americans and were brought to the United States in 1945, where they went to work for the U.S. Army building rockets.
The launch of the Russian Sputnik satellite in 1957, and then Yuri Gagarin's pioneering spaceflight, shook the American government. They were desperate to get an American into space, and von Braun, now working for NASA, was the man to design the rocket to get him there. Von Braun had a choice of fuels. Solid fuel had come a long way since Tsiolkovsky. The new generation of solid rockets, fueled by aluminium powder, were now powerful enough to get into space. But von Braun was wary of them, and with good reason.
The big problem with solid propellants, and everybody said this, is that once you light it, it's like a Roman candle. It's going to burn until it burns out of fuel, and you can't really control it. Wernher von Braun was dead set against using them.
Von Braun argued that liquid-fueled rockets, where the fuel supply to the engine was more controllable, were a better option. He won the argument, for the moment, and the early American astronauts were all propelled into space by liquid fuel. But by the late 60s, it was clear there was a downside to this choice.
It's got turbo pumps turning at 10,000 revs per minute. It's pumping tons of fuel per second through. And all of this has to work under great stress for a few minutes and is then thrown away.
And with a price tag of $185 million on each rocket, this was proving an expensive way to fly. So, in 1969, NASA created the blueprint for an entirely new kind of reusable space vehicle.
It's called a space shuttle that can be hurled aloft piggyback fashion by a rocket up to 100 times.
And to launch it, they came up with a new idea: to combine one high-performance liquid-fueled rocket with two cheaper solid-fuel rockets. But with one stroke, they had broken von Braun's golden rule: never to put a human being on a solid rocket.
He just basically believed that if you put a person on top of a solid-fueled rocket, you're putting them on top of a big firecracker, basically. And that's not something that we should really do.
And here comes the flight crew now.
The shuttle first went into space in 1981. For 5 years, the gamble paid off. Then, during the 25th launch, one of the solid rockets malfunctioned. There's no way to shut off fuel to a solid rocket. The total destruction of the Challenger and its crew was inevitable. Since that tragic day, the shuttle launch system has been refined, but the basic, lethal, combined propulsion system remains. It's far from the ultimate solution. But if you want to get into space, for the moment, rockets are the only way. Once in space, the astronauts need to navigate, and in space, that's trickier than it sounds. The guidance system on the shuttle is scattered about the vehicle, a combination of the most sophisticated technology and the most simple. It takes the energy of 400,000 cars to get the shuttle into space, but once up there, it doesn't take much power to maneuver.
Spacecraft orient themselves and position themselves effectively in orbit by little rocket engines called thrusters. They just squirt out a cold gas, and the reaction moves the spacecraft either in rotation or in translation, actually changes the orbit.
But for astronauts, what's more important is getting back to Earth again. And this is a terrifying maneuver. For if the returning spacecraft hits the Earth's atmosphere too steeply, it will burn up. If the angle is too shallow, it will simply bounce off, back into space. The early spacemen never went far, relatively speaking, and they were safely brought back to Earth by radio signals from the ground. But the 1969 Apollo mission to the Moon was a different matter. They had to get the angle right as they left the Moon, 250,000 miles from Earth. To be accurate over this distance is no easy feat.
I'm going to show you just how accurate the Apollo crew and the mission controllers in Houston had to be to ensure that the Apollo spacecraft returned to Earth safely, did not bounce off the atmosphere or enter too steeply and burn up. This piece of paper is being used to represent the area of the Earth's atmosphere that had to be targeted to achieve that safe return. But not the area that you see, but the area of the edge. And so I'll now walk away to a distance
that will represent the right scale to show you how big that target really appeared from the moon, which is 400,000 kilometers away.
It was like throwing a dart the length of a football pitch to hit the edge of a piece of paper. And they achieved this with a spectacular new invention, created specially for them.
NASA expended enormous sums of money developing what they referred to as the Apollo Guidance Computer, which was an early computer, no question about it. Built at MIT, very sophisticated for its time.
Like explorers from time immemorial, the Apollo Guidance Computer took its position from the moon and stars, but using 1960s state-of-the-art computer technology.
The reality is, your watch, your calculator, virtually anything that you can think of that's got a microchip in it had more computing power than that Apollo Guidance Computer.
It still worked perfectly, bringing Neil Armstrong and his team safely back from the moon. Today, the shuttle computer is more sophisticated, but it still takes readings from the stars and planets to guide the astronauts back to Earth. At speeds beyond the imagination.
If we're coming back from the planets, say on the return journey from the moon, for example, we're travelling at over 11,000 metres per second at 25,000 miles an hour. So these are tremendous velocities. In fact, the Apollo astronauts are the fastest human beings ever, by a long way.
On the journey back from space, there is no margin for error whatsoever. The shuttle must be on target. But even more important, the astronauts need protection. And here, the stakes are even higher. Hurtling towards Earth, the shuttle's astronauts are on the fast track to certain death. Unless they hit the Earth's atmosphere, heat shield first. But in space, it's impossible to tell up from down. So early designers stole an idea from aircraft, the gyroscope.
The gyroscope has the property that it remains pointing in a particular direction, irrespective of what the spacecraft does. And we can use that as an internal reference point.
With a wheel that can move in all directions, a spinning gyroscope will always point the way.
So there we are, the wheel is now spinning. And we can see that as I move the base of this thing, I can move that round, but the gyroscope stays pointing in the same direction. And that's the essential principle. The gyroscope, in some sense, knows which way it's pointing, and it'll remain pointing in that direction, no matter what we do to the spacecraft around us. And this is independent of gravity or magnetic field or anything. So this then gives us our reference direction on board the spacecraft.
And the astronauts can be confident they're not flying upside down as they hurtle towards the Earth. The shuttle is manoeuvred by thrusters, guided by gyroscopes, and controlled by a state-of-the-art computer system to navigate across the huge emptiness of space. Except space isn't really empty. In Earth orbit, there are millions of fragments of rock and dust, known as micrometeorites, which bombard Earth from every direction. Spacecraft need protection, and the shuttle has thousands of individual tiles, multi-layer insulation on the top, and heat-resistant tiles underneath. The shuttle orbits the Earth at 17,500 miles per hour. At this speed, everything is a deadly missile.
Even a grain of sand hitting you at those sorts of speed has tremendous energy and can cause significant damage to a space vehicle.
As early as the 1950s, the pioneers realised spacecraft would need protection. But to design it, they first had to invent a gun that could simulate the high speeds of space here on Earth.
It consists of a barrel, the specific one being 5 meters long, and a breech. We fill the breech with a compressed gas, take a projectile, pull it into the end of the barrel, close it up, and to actually fire the gun, we just turn a valve, and that releases the gas instantaneously.
For the micrometeorite, they used an aluminium sphere mounted in a block. It was then fired at a sheet of aluminium. same gauge as was being used to make spacecraft. If this was the hull of the spacecraft, it would have been fatally damaged. So they tried doubling the thickness. Even this increased protection wasn't enough. The designers had reached an impasse. They couldn't keep increasing the thickness of the metal, or the spacecraft would never get off the ground. Then, Fred Whipple, a professor at Harvard, had a brainwave.
Fred Whipple had come up with the idea that if you had a very limited amount of mass, weight in your spacecraft, it would be very much more effective to have a two-part shield against this kind of impact.
But why does Fred Whipple's theory work?
You had a little thin wall which is just thick enough so that the biggest particles that threatened you would break up, they would explode and they would expand in a gap behind this first plate, so that when they hit the second plate, they were a big cloud, a pressure cloud, which was spread over a much larger area, so the dynamic pressure was much lower, the damage that was done was very much lower.
Nicknamed Whipple shields, this principle of layered protection systems became standard throughout spacecraft construction and is still used today.
That method of protection has been used in many, many spacecraft since, including manned spacecraft, where you have a thin shield, a gap, and then the main protective surface, and it's the gap that gives you the protection.
But a Whipple shield is no protection at all from one of the most hazardous parts of any space mission, re-entry. As a spacecraft hits Earth's atmosphere at 17,000 miles per hour, the impact generates temperatures of 1,600 degrees Celsius. The search was on for a way to protect the spacecraft.
This is a piece of aluminium honeycomb, and it's typical of the kinds of materials we use to construct spacecraft.
The burner heats one side of the aluminium sample with the energy of re-entry. The temperature taken on the other side represents the interior of the spacecraft.
We can immediately see that the aluminium starts to glow. In fact, we've got an orange glow now. Actually, we're melting all the way through the aluminium. So obviously, if this is the spacecraft, the walls of the spacecraft are breached, the atmosphere will leak out, and the astronauts will be in very serious danger.
To protect spacecraft from these extremes of heat, in the 1950s, Russian scientists came up with a remarkable solution based on a process called ablation.
In an ablative heat shield, we deliberately let the outside of the spacecraft burn. It sounds strange that that is actually a cooling process, but it is. This is
All kinds of materials have ablative properties. In this test, natural cork is protecting the aluminium. As the ablative material burns, the energy of re-entry is used up and the astronauts are kept safe.
I'll turn on the burner. Immediately you'll see we get a flame. No doubt there are chemical changes happening. You'll see that it's glowing red hot in the middle, but the remarkable thing is the temperature of the aluminium is not changing. It really is doing its job. Now that flame that we see is exactly what we get in real spacecraft. As the spacecraft plunges into the atmosphere, it's bathed in fire.
But the astronauts inside survive. Russian cosmonauts still use this technology every time they return to Earth.
This 1960s technology of the ablative heat shield is really effective. However, it is a one-time only system. Once we bring the craft back, the material is destroyed.
So it wouldn't work for the shuttle. Its protection system, like the vehicle itself, had to be reusable and light.
They thought about using an ablative heat shield like they had used on Mercury, Gemini, and Apollo, but it was just too heavy. So they had to come up with something that was much more lightweight. The tiles were the answer.
Made from silica, they have an almost powdery consistency. Individually shaped and numbered, over 34,000 tiles fit around the shuttle like a huge jigsaw. And their insulation properties are remarkable.
Nose gear touchdown.
So we turn on the heater. And immediately you can see this bright orange glow from the heat on the front of the tile. But as the thermometer shows, very little change in temperature. In fact, now it's really beginning to glow almost white hot. If I turn off the heat, remove it, you can see that it's cool to the touch. It really is a super insulator.
February 2003, the Space Shuttle Columbia explodes on re-entry. Immediately, suspicion fell on the heat protection system. For 7 months, accident investigators scoured the Texas countryside for the wreckage. Then they reassembled it in a vast hangar at the Kennedy Space Center.
Ignition and liftoff of
They examined TV footage of the launch, and there they saw the moment when the fatal damage was done. The silica tiles have remarkable insulating properties, but they are incredibly fragile. Worse still, unlike the ablative heat shields, they are vulnerable to damage at launch.
The fact that they are exposed during the launch has also been an issue, and during every flight, some of those tiles, because of the jarring associated with the launch, are lost. They fall off. The adhesive fails.
When the accident report was issued, it confirmed that some tiles had been damaged at launch, as had happened before with the shuttle. The difference this time was precisely which tiles had been damaged. They were tiles on the left wing, at re-entry one of the hottest spots on the entire vehicle.
This created a gap in the thermal protection system that on re-entry allowed hot gases to come into the wing and burn and melt the metal components underneath, collapse the wing. The spacecraft began to tumble and it broke up.
Despite the Columbia disaster, NASA has no plans to rethink the shuttle's protection system. In future, spy satellites could check for tile damage once it's in orbit, and if necessary, astronauts will be rescued by another shuttle. Re-entry remains the greatest challenge in the battle to build the ultimate protection system. For 40 years, space scientists have struggled to build the ultimate spacecraft. The shuttle is today's cutting edge, but even the space program's most enthusiastic supporters admit it's far from perfect.
The space shuttle's been flying now for more than 20 years, and it's become painfully aware to us, especially in the aftermath of the Columbia accident, that it is an aging vehicle.
Not only aging, but also very heavy. A smaller rocket is a safer rocket. So in the future, NASA plans to launch entirely separate rockets for the equipment and for the human cargo.
NASA's already named the orbital spaceplane. It's not going to be a hauler of large payloads like the shuttle was. We can use other vehicles for that, but it will haul people. And that's going to come online within the next decade.
The exploration of outer space is still a dream, but a journey to other planets could be a reality with new, safer propulsion devices.
The most complex ones, the ion thrusters, which has an exhaust velocity of 30 kilometers per second, and this can enable you, particularly for deep space missions, to actually get there, to get to Mercury, to get to Jupiter, to get to those sort of planets.
50 years, billions of dollars, many lives lost. Still, space exploration continues to captivate presidents and generals. But the mission to build the ultimate spacecraft remains elusive. This is a machine built to intimidate.
This terrifying, growling, noisy beast that can smash its way through buildings, uproot trees, crush cars.
These things look invincible. You can't see any damage being done, and you leg it, and why not?
14 of these vehicles turning up will completely ruin your day. They are fearsome.
The tank, the bully on the battlefield. Inspiring affection.
This tank saved my life and those of the crew.
Constantly evolving in a race for supremacy.
In this never-ending battle between weapon and armour.
Its design driven by the enemy's desire to destroy it. Defying the doubters, the tank still holds its own on the battlefield. Perpetual testing, reinventing, in the search to build the ultimate. This is the Challenger 2, pride of the Royal Armoured Corps. 69 tons of precision-cut steel, an engine as powerful as 10 Land Rovers, and a gun that can annihilate targets miles away.
There's a lot of noise and dust and diesel fumes and confusion for us, considerably more for the enemy. These strike fear into the hearts of anyone who's sitting in a trench waiting to be attacked.
The tank is the culmination of nearly 100 years of evolution.
There are three components that make up a tank, that make a first-class tank, and they are protection, firepower and mobility. And one must have an equal balance between these to make the tank a superb fighting vehicle.
Mobility gives the tank its uniqueness as a weapon of war. It allows unrivaled command of the battlefield. Strip away the tank's armour and gun, and its true genius is revealed. The tank, as we would recognise it today, first rumbled into view in World War I. The British unleashed their new wonder weapon on an unsuspecting enemy.
One can almost imagine what it must have been like in 1916 when the Germans, peering out of their waterlogged trenches, saw these great armoured monsters trundling towards them. No sign of human beings, this terrifying, growling, noisy beast that can smash its way through buildings, uproot trees, crush cars with impunity.
The days of trench warfare were numbered.
The Germans were digging trenches at least 9 feet wide. So the designers solved the problem by literally increasing the size of the frame of the vehicle and then wrapping the tracks all the way around. And what it means is that on rough ground, this vehicle will present a tracked surface, a moving track, at virtually any angle, from nose down to nose in the air. There's always something to grip and keep it going.
Tracks have to withstand huge stresses. They have to be able to climb steep gradients, keep moving through water, and plough through desert sand. Track design has been much refined since World War I, but the big change came in the 1970s, and it's invisible. In 1916, tracks were made of cast iron. Today, they're a complex mix of steels.
We have to control the type of steel that we use in each individual part so that it's strong enough to do the job. And the way we can do that is by controlling the chemistry of the steel.
Some parts of the track have to be flexible, others demand pure hardness. Track technology has come a long way. This strength test shows just how far. 2 track links have been made that look virtually identical. One of modern steel, the other cast iron. Both will be tested to breaking point.
We would expect the modern track link material to sustain a load of around about 18 or 20 double-decker buses being loaded onto it in this central section.
First into the test rig is the cast iron track link. It buckles under a force of 21 tons. Next up is the modern steel track link. It fails at an impressive 40 tons, withstanding twice the force of the cast iron.
The historical material has failed catastrophically, and it's actually broken all the way through the link. Whereas the modern steel material, not only has it carried twice the load, but also it's been able to bend whilst it's carried that load before it's broken.
So track strength has increased massively since World War I. The other great advance has been in suspension.
In the First World War, tanks had no springs at all. And the big advance in suspension systems was that introduced by J. Walter Christie in the 20s.
J. Walter Christie was a freelance American tank designer, considered by many to be a genius, by others to be a complete maverick. And Christie's ideas for suspension were by far ahead of their time. There was nothing else like it in the world.
Now, if you can imagine that my forearm is a swinging metal arm attached to the tank here at the back, and with a wheel roughly where my hand would be gripping there. That arm has bearing upon it an enormous coil spring. So, tank reaches a bump, wheel rises up, pushes up the arm, spring pushes it back down again. One of the characteristics of the Christie tank is the gap between what's known as the top run of the track and the tim work, enabling the wheels to move very freely. So with a tank like this, you could easily do 30 miles an hour across country quite comfortably. Indeed, in 1932, Christie had a tank doing 60 miles an hour over rough ground. Nearly finished off the driver, but at least it could do it.
A 30-foot trench in front, and she's over.
While steel technology transformed tracks, independent suspension turned the tank into a highly mobile fighting machine. Tank design is constantly evolving, but one problem has never gone away. A tank has to be able to take a hit. In World War II, British tank designers believed sheer thickness of steel was the key to protection. Come D-Day, their hopes were pinned on the Churchill tank.
It was the most heavily armoured tank that the British had at that time, and the front plate was about 6 inches thick.
Dennis Kerner was just 18 when he joined the Royal Armoured Corps. In August 1944, in its first real battle, 2/3 of his regiment's tanks were knocked out in barely 2 days.
I've seen the driver and the co-driver, after their tank had burnt out, trying to escape through the escape hatch, and they were burnt to a cinder, and all you could see was the grey matter of their bones as they'd stretched out, and that is not a pretty sight. When we came up against these German tanks, you were not prepared for what they could do. I mean, our shells would just bounce off.
But why were the shells bouncing off? The answer? An innovation the Germans had copied from the Russians, and one still used in virtually every tank today. A simple but brilliant idea. Slope a tank's armour, and its thickness is effectively increased.
I've got 3 pieces of identical armour here. In this one, a projectile can defeat that if it gets across the width. In this one, because it's sloped, the effective width has now increased. And for any projectile, it may not get through. Now, if you slope it even further, you might be protected again by the projectile not being able to penetrate, but ricocheting away off the surface.
Testing at a firing range should show why sloped armour is so effective.
Now what we're going to fire at is this. It's armour plate, about 15 millimetres thick, made of solid steel. Now although that represents quite a challenge, it's my guess that this bullet, travelling at 890 metres per second, when it hits it, will penetrate.
Test 1. A piece of armour positioned vertically. Test 2. Armour sloped at an angle of 30 degrees. And finally, test 3 at 60 degrees.
This is the first plate that we fired at vertically. And what we've got is a clean penetration. Hole at the front, clean hole straight the way through to the back.
Here's the impact again, viewed this time through an ultra-high-speed camera. The vulnerability of the vertical armour is plain to see.
Where we put the plate at 30 degrees to the vertical, we've actually caught the bullet within the armour, and you can see the base of it there. And we've got a bulge at the back, but no penetration. So it wouldn't have caused any damage on the inside.
On the high-speed images, it's clear there's no penetration.
And lastly, where we slope the armour right back at 60 degrees, we've got a dent, but there's no bullet. It's ricocheted clean away. And again, no damage to the inside. So the effect is that by sloping the armour, we've protected the crew, although we've only kept the same thickness of steel.
But new armour designs always provoke a counterpunch. Before World War II was over, an anti-tank weapon was invented that could penetrate even the best sloped armour: the shaped charge. Tank armour design has to be constantly rethought as new weapons are devised to defeat it. Most deadly of all is the shaped charge. Invented at the end of World War II, the shaped charge was unchallenged for more than 20 years. But in 1967, a chance discovery tilted the balance back in favour of the tank. A young German scientist was experimenting with captured Egyptian tanks in the desert.
It was after the Six-Day War, where Israel have destroyed a lot of Russian tanks from the Egyptian force, typically T-54 and T-55 tanks. I wanted to see the effectiveness of my warheads on real targets.
Manfred Held was testing shaped charges against tank armour, but he was puzzled by the results.
This was a surprise that my shaped charges was not able to penetrate the total turret, and I wanted to find out at once what was happening.
He discovered that there was still live ammunition in some of the tanks. As the shaped charge penetrated the armour, it hit shell cartridges on the inside, causing them to explode.
After the test, I found no impacts on the other side, only the entrance hole, and burned our cartridges, but nothing else on the other side. And this was against my prediction.
Manfred realised he was on the verge of an important discovery. He inserted high explosive between two metal plates and placed it on the tank's armour. The impact of the shaped charge was drastically reduced. Manfred patented his design in 1970. It would revolutionise tank protection. He had invented what's now known as explosive reactive armour.
This is a shaped charge. Now we're going to fire that against these steel plates. And between the two, I've placed a block of polystyrene that will give it the standoff required to give it the most effect. Now across here, I've constructed the same sort of experiment, but on this occasion, between the two, I've inserted a layer of explosive reactive armour. Now this is constructed from two steel plates, but sandwiched between is a sheet of plastic high explosive. When the jet fires down into those plates, it'll detonate the plastic explosive and the two plates will fly apart. Now the effect is that the jet has to cut its way through these plates and is essentially disrupted by that and will hopefully show far less penetration down in the armour. Now, as we saw, there was a huge release of energy in those explosions. Massive damage done. This was the one where the shaped charge did a direct attack onto steel blocks. And we've had penetration all the way through to this block here. Now, in this set, where we had the explosive reactive armour, we've only got penetration down to the 5th block. We've saved 3 whole blocks of penetration, but ultimately, the explosive reactive armour has saved that crew's life.
Explosive reactive armour gave tank protection a whole new dimension and a crucial edge over the weapons designed to penetrate it. A tank's main purpose is to take and defend ground. A powerful and accurate gun is vital. Wartime newsreels often show tanks firing on the move. The reality was that few tanks could fire accurately like this. In fact, most fired from a static position.
Basic principle of firing a gun from a moving object is not a new one. The Royal Navy had this problem hundreds of years ago when it tried to fire cannon against other ships on a moving sea. and it's really just the same problem that we have in tanks. In the Second World War, it relied on great skill and experience of the gunners to achieve some sort of accuracy.
American tank designers were working on the ultimate solution. By 1945, they'd introduced stabilization systems on their tank guns. Today, these use gyroscopes to sense the tiniest movement and correct it with sophisticated stabilizers.
That enables us to lay the gun onto a fixed point, and the gun will remain pointing at that point regardless of what the vehicle is doing. So even if the vehicle is moving along an extremely bumpy or undulating surface, the gun still remains fixed on the point of aim.
So modern battle tanks can hit targets several miles away with pinpoint accuracy. Whether moving or still. Supreme weaponry makes today's tank a fearsome machine. To reach speeds of nearly 40 miles per hour, the Challenger 2 needs a mighty engine. 1,200 brake horsepower drives these monsters along. But power and speed are useless if a tank keeps breaking down. A key lesson in tank engine design was learnt in the winter of 1941. The German armoured divisions were fighting on the Eastern Front. To their dismay, their once all-conquering panzers ground to a halt.
The onset, of course, of the Russian winter completely broke down the German armoured thrust. The Germans suddenly found that their entire tanks' cooling and lubricant systems and fuel supply became completely iced up in temperatures of minus 40 and 50.
The myth of German tank invincibility had exploded. Their sophisticated engines failed when the mercury plummeted. The much simpler Russian tanks just kept going.
This is the Russian T-34, probably the key tank of the entire Second World War. The engine is the crudest, toughest old V12 diesel you could possibly imagine, a thing that will slog on in the worst possible conditions.
Nearly 60 years later, Russian tank engines are still going strong. One of them in this quiet corner of Devon. Preston Isaacs collects tanks. This is one of his favourites. A genuine World War II T-34. Ex-tank commander Mark Corby has come to get a feel for this rough but reliable piece of Russian engineering.
Carefully does it. Very elegant.
God, it's brutally basic in here, isn't it?
Yes, welcome to a luxury vehicle.
Where's all the padding gone? I mean, what's it like this?
It's not enough to bang your head on, but everything is very basic. Don't waste time grinding bits off. Make it in a hurry, make it work, and that's all you need it to do.
This is the, what, the gear lever here?
Gear lever. That's your machine gun.
Right, yeah. Oh, yeah.
And that's your sole view of the world, what you can see through that.
Okay. Shall we go?
Shall we be away?
Okay.
The T-34 signalled a turning point. From now on, simplicity and reliability would be the key ingredients. Today, most modern tanks have diesel engines, but Mother Nature keeps on throwing new spanners into the works. Oman 2002. The British Army is on a massive exercise in the desert, but its tanks keep breaking down. At the Armoured Trials and Development Unit, they tried to find out why.
Basically what was happening was that the dust, which is very fine sand, was coming up between the road wheels and swirling up underneath the skirts and on top of this air intake and basically being sucked straight into the engine.
Tanks have been successfully operating in the desert through 2 world wars. So why was the state-of-the-art Challenger 2 running into trouble?
The normal wind-blown sand is quite coarse and each particle is very clearly visible. But when that sand is trafficked and vehicles have been passing across it for a while, it becomes extremely fine and powdery, almost like flour. And it is this fine dust that is what was posing the problems to the vehicles.
The wrong kind of sand? Sand in Oman is not the same as that in North Africa. The aerodynamics of the Challenger 2 was creating a wind vortex that drove this superfine sand into the engine.
Whenever we go to war, we suit ourselves up in this armour, and just by doing that, we change the dust vortices to such a degree that we move them back a degree, but we still had that problem. So we came up with this idea here, which essentially is a number of canvas skirts joined together with some clips. And what that does is it forces those dust vortices down and keeps them down as the tank moves forward until the tank has passed over and they appear behind the tank. So you get a great plume of dust behind the tank, but not being sucked into the engine. So a simple solution, but one that we're very proud of.
Ingenious yet simple answers to complicated problems. This is the tank of today, but what is its future?
The big question, of course, is the tank still relevant then? Is it really an obsolete piece of junk that can be shot to pieces by air power?
But aircraft have their own limitations.
You can never dominate the ground, really, by air power. You can make a mess of it, but you can't really dominate it. If you want to dominate the centre of a city, you've got to have a tank in there.
So the tank has timeless qualities.
Rumours of its demise are much exaggerated. I have to say this thing will turn up on a battlefield for the foreseeable future.
But change is still on the cards.
One can see far more concentration, I suspect, on lighter, more mobile vehicles that are air-portable for a start, to get to a trouble spot quickly. And I do think what we will see is the tank being upgraded and improved rather than redesigned.
Evolution continues, but the essentials remain the same. The modern passenger jet. It flies at over 600 miles an hour, high above the weather. It can cross the Atlantic in 6 hours, and it's the safest form of transport by far. It's 50 years since the passenger jet first transformed our world.
It was really breaking new ground. Nobody had ever built anything like this before. What it meant for the guy in the street was that he could fly almost as fast as a jet fighter at the time.
Today, the battle continues to design planes that are ever faster and more efficient. Designers are constantly testing new materials and pushing at the boundaries of aeronautical understanding.
When they see the swept blade, they'll go, gosh, that's different, because it will be so different to what they've actually seen before.
Is it as perfect as it can be? How close are we to building the ultimate passenger jet? This is the Airbus A330, one of the most advanced passenger jets in service. It carries 360 passengers, over 300 more than the first jet airliner. And a single Airbus engine produces enough energy to supply a small town. The modern passenger jet is a miracle of engineering. But the design journey to get here has been an extraordinary story of inventiveness and disaster. From the beginning, the dream of aircraft designers was to build a passenger plane that combined the comfort and style of old world travel with high-tech, high speed. In the 1940s came an invention that would revolutionize air travel: the jet engine.
This was an exciting time. Jet engines really were the news. They were being featured all the time, jet aeroplanes being featured in the newspapers and in the news. They were breaking new records. This was a revolutionary mode of transport.
And the first passenger aircraft to use jet engines was the Comet.
But it was the Comet which attracted most attention as it took off.
The Comet in one stroke, almost half the time that you could actually get to somewhere. For example, the first flight, the world's first ever jet passenger service from London Heathrow to Johannesburg in South Africa on May the 2nd, 1952, took 18 hours compared to 32 hours previously. So it really was a major step forward.
From the invention of the jet engine, designers have had one aim: to make it both powerful and fuel efficient. A state-of-the-art jet engine takes 15 days to build and costs around $10 million. It has two essential parts: the motor and the fan.
For any aircraft to fly through the air, it needs some form of propulsion, and the simplest form is a child's balloon. You fill the balloon with air, then when you release it at the nozzle, the air escapes, pushing the balloon along.
With a jet engine, the air is collected by a fan that's driven by the motor.
This fan collects about a ton of air a second, propels it rearward, and pushes the aircraft along through the air. The ton of air is collected every second, and that's enough air to empty probably 2 swash courts in a second.
To travel faster, designers knew they needed to get more air through the engine. This quickly became their holy grail. In 1950, a jet engine fan blade was about 12 inches long. Designers knew the simplest way to move more air through the engine was to increase the size of the fan blades. But as they increased the size of the blades, they were simply creating another problem for themselves. Bigger blades were heavier. So in the 1970s, the race was on to find a way of making these bigger blades lighter. The answer? Make them hollow. These hollow blades were fitted in 1984 on Boeing 757s and later the 747s and Airbus A320s. But making a hollow blade isn't easy. Designers at Rolls-Royce found that the two panels would flex and vibrate. To stop this happening, they came up with an ingenious solution.
The need was to have a blade made up of 2 titanium panels with a honeycomb core inside to stop the panels from vibrating together, so what I would call panting, so they're moving together relative to each other.
But hollow blades weren't the end of the story. In the 1990s, in search of the ultimate engine, Hilary Barton and her team looked to computer-aided design to improve the shape of the blade itself. They came up with a radical new design, a swept blade. And they managed to make blades lighter still by changing the way they are built.
The latest blade is manufactured from basically 2 sheets of titanium panel with a third one in the middle. So they come together and that basically forms a sandwich with a filling in the middle.
Then a second manufacturing process works its magic.
Extreme heat is applied to the sandwich and an inert gas is pushed into the sandwich and it causes the external panels to form, to blow out, to inflate.
And that makes the titanium core stretch between the two panels into a unique structure.
And in stretching it forms a corrugated internal core which has like a zigzag form.
A form that makes this state-of-the-art jet engine both light and very strong. But it's the groundbreaking blade shape that Hilary Barton thinks catches passengers' attention.
I think to people that go and actually look at the front of an engine, when they see the swept blade, they'll go, gosh, that's different, because it will be so different to what they've actually seen before.
After 50 years of design improvements, the jet engine is more powerful than ever. But it also needs to be proof against a surprising hazard: birds. Since the earliest days of flight, birds have been a danger.
The very first bird strike actually happened to the Wright brothers back in 1908, where I believe it was Orville Wright's Wright Flyer hit a gull. The first fatality was in 1912 when Cal Rogers, who was also flying a Wright Flyer, had a gull entangled in his aircraft controls and he unfortunately died as a result. And bird strikes have been occurring ever since.
With the advent of jet travel, things changed. Sometimes bird strike would bring the plane down, sometimes it wouldn't. Then a plane crashed on takeoff at Boston Airport and 62 people died. When bird strike was suspected, ornithologist Roxy Laybourne determined to solve the mystery. She began to examine the remains of birds that had struck planes, trying to establish if there was a pattern to which birds were the most dangerous. But immediately she hit a snag.
Frequently these remains are completely shredded. They've often been cooked due to the high temperatures involved. They're almost like shredded pipe tobacco in texture.
The usual bird identification techniques are useless with such mangled specimens, but the ornithologists were able to turn to the latest stereo microscopes to gather clues.
This can be done with even the most tiny fragments of downy feather from a bird. Then we can look at the microscopic structure of the bird's feathers, and we can compare this to reference material that we have here at the laboratory to match groups of birds with the unknown bird.
As more and more samples arrived in the lab, Roxy Laybourne began to identify a pattern. The crucial factor was not the size of the bird, but whether it was a bird that flocked, like gulls or geese.
Solitary species, birds such as kestrels, for example, that might hover over airfields, are far less hazardous to aircraft because they occur on their own. They can only ever hit one engine.
It was the multiple strike, more than one bird being sucked into an engine at once, that would bring a plane down. Armed with this new information, blade designers began to engineer their blades to counter the real threat birds posed. Every new blade is tested to withstand impact from a 4-pound flying goose. This Rolls-Royce blade is designed to dissipate the energy of impact. It flexes and only takes 2 rotations to return to normal.
Once it's rotated once or twice, the blade has returned to its start shape and is really hardly affected by the impact at all.
But this test only represents a single bird and a single blade. Can a complete working engine, $10 million worth of cutting-edge technology, survive the ultimate test, the worst-case scenario, a multiple bird strike? Before it can fly, every new jet engine must survive the ultimate test, a multiple bird strike. A fully working engine with a value of around $10 million is mounted in a test rig, and 6 chicken carcasses are fired at it.
Clearly, we can't move the engine forward at the takeoff speed of an aeroplane, so we have to fire the birds into the engine at that speed.
6 barrels use compressed air to fire the birds into the engine.
Now, the objective here is that the engine continues to operate and it mustn't lose more than 25% of power.
6 birds are fired. There's a slight note change as the blades flex, but the engine only loses 3% of its power, so this takeoff would have proceeded smoothly with no risk to the passengers on board. Thanks to the forensic detective work of ornithologist Roxy Laybourne in the 1960s, all jet engines are now engineered to withstand multiple bird strike. 50 years ago, the jet engine transformed air travel. Today, it's astonishingly powerful and super light. It's the beating heart of the passenger jet. Since the first flights in 1903, engineers had used paper, cloth, wood, and eventually aluminium to make aircraft. But to get the best out of a jet plane, it should fly at 35,000 feet, where temperatures are minus 40 degrees. This would test aluminium to the limit. (1952), the first commercial flight of the world's first passenger jet takes off.
Designed to fly at a speed approaching 500 miles an hour, it represents the first of a new generation of jet airliners.
To make passengers comfortable at 35,000 feet, the Comet had to be pressurized and light enough for the first generation jet engine.
Jet engines, the initial jet engines, were not as powerful as ones that came on later on, so they had to make the construction as light as possible.
To achieve this, Comet's designers made the aluminium exceptionally strong. They did extensive tests to confirm it could stand the stresses of pressurization. There was no hint of trouble. For a year, the Comet flew safely. Then in 1953, disaster struck.
During 1953 and 1954, the Comet unfortunately suffered a series of disastrous accidents.
The whole fleet was grounded, and accident investigators began to search for clues to what had gone wrong.
As parts of the Elba comet were recovered, they were immediately flown back to Farnborough, where the intricate job of identification and assembly began.
For months, they examined the wreckage from the comet accidents and submitted a working plane to extensive testing. The fault they discovered has since become famous: metal fatigue. The comet designers had chosen aluminium alloys that were very strong, but it turns out that this was precisely the problem.
Because the fatigue problem was not fully understood at that time, they would have not have had the full knowledge that we have today about the fact that when you design alloys for very high strength, it could make them more prone to this fatigue cracking problem.
Intensive research into metals and how they behave in flight followed the comet tragedy. It caused a step change in plane construction.
The lessons learned from the experiments and the investigation was that the metal needed to be thickened, and also some of the aluminium actually used need to be changed, and the lessons learned from that were put into the development of the Comet 4.
The alloys used in Comet 4 were the product of this intense research. Martin Painter is a true enthusiast. He's not only knowledgeable about the comet, he's also got a bit of it in his garage.
Well, what we have here is two sections of a former BOAC Comet 4. The aircraft was part of the fleet that started the very first transatlantic jet services back in 1958, and I managed to pick up a couple of mementos.
A sample of Martin's memento was taken to be scrutinised by an expert. It was to prove impressive.
When we tested the comet material, we're surprised at the high level of strength that we achieved on the tensile specimen. The comet material is in fact comfortably within the current requirements for that type of alloy.
The strength-to-weight ratio of the aluminium alloy used to make Comet 4 is still the best it gets.
It's not surprising that this material is still used for the manufacture of aircraft today.
What the comet disaster taught aircraft designers was not just the danger of metal fatigue. They also learned to tailor their use of metal alloys precisely to the different parts of the aircraft.
So you would use alloys which are tailored for high strength in the top surface of the wing, and you would use alloys which have good fatigue properties in the bottom surface of the wing.
The Comet 1 tragedy shook aircraft designers to the core. It revolutionised their understanding of how a plane can be made lightweight, but also safe. A passenger jet can't be made entirely of metal. The pilot needs to see where he's going, and it's nice for the passengers to see out too. On the ultimate passenger jet, windows would be tough as steel and light as a feather. They haven't achieved it yet, but it's this goal that for half a century has driven glass manufacturers.
Back in the 50s, the technology was the limiting factor in reducing the weight. So they used the best available technology at that time, which was conventional air toughening.
Glass made this way had been used on propeller planes, but now everything had changed. Jet flight demanded glass that was lighter and stronger than this air-toughened glass. So the race was on for new ways to make glass stronger. The way to toughen glass is to get the heat out of it quickly. In the 1970s, 20 years of experimentation by Pilkingtons in Birmingham paid off. They came up with a radical new way of doing this. To this day, the key to how it works is a closely guarded secret.
The glass comes through on the tongue bar system. The furnace door then opens. The glass goes up into the furnace. It's up there for probably 2 to 3 minutes at around 600 degrees C. It then comes down out of the furnace, and then it goes down into the powder. It looks like a liquid, but it's actually a powder which is fluidized by air bubbling through it, which allows the glass to slide into it when it comes out of the furnace.
This remarkable powder is very effective at removing the heat and so toughening the glass. So what's it made of?
Unfortunately, I'm not able to tell you the formulation, the chemical formulation, because it's company confidential. So.
The latest technology can produce glass that is half the thickness of 1950s jet plane glass. And just how strong it is astonishing. In this one-off experiment, a vehicle weighing nearly 1,000 kilograms will be lifted off the ground. The whole weight will be supported on a single piece of glass.
This is a chemically toughened piece of glass. It's been toughened by immersing it in hot molten salts, and it's 8 millimeters thick.
The glass bar is placed into the lifting rig. The crane lifts the rig until all the slack has been taken out of the chains and supports. The next stage is for the 8mm glass bar to take the full weight of the car as it's lifted from the ground. The most modern technology, the most demanding conditions, a dead weight of around 1,000 kilograms on a single piece of glass. The ultimate jet needs materials that are light, strong, and tested to destruction. But what about the shape of the passenger jet? The body of the jet has hardly altered in 50 years, but the wings have been transformed dramatically. Changing the wing shape is a tool that designers can use in their ongoing battle to make jets ever faster and more fuel efficient. Where the Comet had wings that were at right angles to the fuselage, by 1960, jet wings were at quite a different angle.
The first generation jet airliner wings were basically similar to the ones that were used on the propeller aircraft. What was needed was a wing that would limit the increase in resistance as the aircraft flew faster and faster with jet engines.
These thinner and more swept back wings enabled jets to fly faster. But as the planes flew ever faster, designers discovered they had created a new problem to grapple with. When any aircraft is flying, the air moving over the top of the wing travels faster than the air going underneath. As jets approached the speed of sound, something started happening on the tops of the wings that was very worrying.
The airflow over the top of the wing would actually go faster than the speed of sound, and would, somewhere on the top of the wing, you would get a strong shock wave, which give a lot of drag and is unacceptable. You must fly with very little shock drag on the wing.
To eliminate drag, Jeff Jupp and his colleagues experimented in the wind tunnel. First, they increased the sweep of the wing still further.
It was realised that by sweeping the wing backwards, rather like on this more modern aircraft, the A330, see the wing is not perpendicular to the fuselage but is now swept back. That also helped to reduce this problem of the shock waves formation as you fly faster.
Over more than a decade, they continuously modified the shape of the wings until at last they cracked the puzzle.
We were able to use the new computer programs to design the airfoil theoretically and then check it out in the wind tunnel to just check that we got what we were designing. And indeed, the results were very good.
They had designed the supercritical wing.
It takes a little bit of thinking about, but the flow is actually supersonic over much of the wing, even though the aircraft is still flying below the speed of sound. And this is done still without getting these severe shock waves, which would give uneconomic flight.
And this ingenious technological marvel is now the design choice of aircraft manufacturers everywhere. Modern wings have achieved the ultimate combination: higher speed for less fuel.
The Comet really did usher in a totally new form of transport.
And ever since, aircraft designers have been refining that basic concept. This may be the final variation on the theme, the 800-seat double-decker Airbus A380.
This is a very large aircraft. It is probably getting pretty close to the maximum size of aircraft that we would envisage with today's materials and techniques.
Radical alternatives are being explored, but for now, this is probably as close as it gets to the ultimate passenger jet. Malaysia. These are the Petronas Towers, the tallest skyscrapers in the world. The skyscraper is a great engineering achievement.
They have to deal with gravity, they have to deal with wind.
These shining towers of steel, concrete and glass are tested to their limit.
They have to deal with earthquakes, they have to deal with fire.
Now they even have to deal with terrorist attack.
What engineers now are doing is having to think the unthinkable.
Can we build the ultimate skyscraper? Skyscrapers reach for the sky. Mankind builds them ever higher and higher, testing his ingenuity against the forces of nature. This is the Swiss Re building in London. It's nearly 600 feet high and known as the Gherkin because of its curious shape. This aerodynamic design is the cutting edge of skyscraper thinking. The modern skyscraper was born in Chicago.
In order to understand the development of the skyscraper, we really need to go to Chicago, where in the 1880s, some of the most significant developments occurred in the history of the skyscraper.
Evolution came out of disaster.
Chicago was destroyed by fire in 1871, leveled in fact. The central part of the city was gone. And for a city that was exploding in population and very wealthy with a burgeoning commerce, it was important for the city to rebuild as quickly as it could.
So they decided to build tall. The jewel in the crown of reconstruction was the Home Insurance Building. It rose 10 stories high, dizzyingly tall for the time. The era of the skyscraper had begun. But some think the evolution of skyscraper structure has its beginnings long before. This is Salisbury Cathedral in the heart of England. At 404 feet tall, it's more than twice the height of Chicago's Home Insurance Building. When finished in 1320, the world had seen nothing like it.
The spaceship, this is a NASA project of its day. Something that took 100 years to build. It had hundreds and maybe thousands of people working on it through that process. There was so much humanity invested in it.
Chris Wise traces the origin of the skyscraper to this brilliantly conceived medieval structure.
Well, this is a building I've been back to pretty much every year for the last 25 years, and the reason is that it has all of the essential ingredients of a modern skyscraper inside it. But unlike a modern skyscraper, you can see it all.
The first priority for a very tall building is to carry its own weight. Salisbury's designers came up with a structure that would set the standard for future skyscrapers.
The spire is a very, very early example of what's called a monocoque construction. And it may not look like it, but this spire is exactly the same sort of structure that we still use to design skyscrapers when we get up above 60, 70 stories tall. So every 100-story skyscraper that anybody ever thinks of uses a monocoque in some way or another.
Monocoque design means using a single shell and involves the external walls carrying all the weight of the building, but it does more.
It uses the whole of the skin of the tower to resist all of the forces, to carry its own weight, but more importantly, to resist all the sideways forces from wind. And you can hear the wind outside now, blowing on this, and it's been blowing here for 800 years, trying to knock this spire over.
Chicago is nicknamed the Windy City. As soon as architects began to build tall there, they discovered that wind was a deadly enemy.
If you take a building that's fixed down to the ground, the load from its own weight just goes down inside it, through all the structure, into the foundations. But the wind load is trying to push it over sideways.
Skyscraper engineers quickly realised that they couldn't just design for average wind speeds. their buildings had to withstand hurricane force.
The wind that engineers design against is the worst gust of wind that might only last a few seconds, that blows perhaps on average once every 50 years or once every 100 years. So you're designing the whole building for the whole of its life against an event that will perhaps happen just once in the whole life of the building and only last for a few seconds. But that's what wind design is all about.
Beneath Salisbury's spire, it's possible to appreciate the force of the wind.
On a really strong windy day, I've worked out there's around about 50 tons of wind blowing sideways on this spire, trying to knock it over, which is not trivial. It's one of the things that tall building designers have to think about all the time.
There's another trick the skyscraper pioneers came up with. But once again, the medieval builders got there first.
They realised that they could use the scaffolding to their advantage, and although it looks as though it's holding the spire up, it's actually only attached at one position, which is right at the very, very top. And it pulls down on the top of the spire and basically stabilises it against the attempt of the wind to push it over. That's very clever. That's called pre-stressing. That's something that people only started using seriously in modern structures in about 1900. So, I mean, these guys are well ahead of their time.
Pre-stressing gave the skyscraper extra rigidity against wind, but it only works up to a certain height. The soaring towers that were built in New York in the late 1920s were the first skyscrapers to pass 1,000 feet. With that height, they had to have very strong central cores to counteract wind. This is the 70-storey Trump World Tower, the state of the art. It's designed by Ahmad Rahimian, a rising star in the new generation of structural engineers.
This building currently is the tallest residential building in the world. It has about 862 feet high. It's about 263 meters. And in order to build a building of that height, there were a lot of new technology introduced in the building.
A key innovation is how it deals with wind. It does more than just resist, it actually cancels it out. A skyscraper that sways a little in the wind may be structurally sound, but the human beings inside can quickly feel sick. This top-floor apartment is priced at $15 million. Whoever buys it expects it to stay still. To ensure this, Ahmad has installed an ingenious device. It's called a tuned mass damper. In effect, it's a huge counterweight, a massive 600-ton block of solid steel, surrounded by shock absorbers.
This element that you see here is similar to the shock absorbers that you would have in your car. However, much more powerful and sophisticated. Imagine we would have a 60-mile-an-hour wind approaching the city and the building. What you would see is that this block of mass starts moving in its own natural mode, back and forth, and as a result, exciting this series of shock absorbers and dampers, which transmitting forces to the building opposite to the direction of the wind. And as a result, it would cancel the wind pressures applied to the building and suppress the building's motion.
So the evolution of structure has solved the problems of weight and wind. But structure alone was not enough to create the modern skyscraper. Two key developments in the 19th century had to come first. One was the elevator.
Suddenly, almost overnight, it became possible to move things from ground level up pretty much as high as you liked. And so people started thinking, well, maybe we could build higher if we wanted to.
With the invention of the elevator, tall buildings could reach higher than ever before. But immediately, engineers hit a problem. For all its ingenuity, Salisbury Cathedral has one fundamental flaw. Soon after the spire was added, its masonry structure began to show signs of stress.
Well, it's amazing. Above me is about 10,000 tons of cathedral, and it's piling down through this column. There are only 4 of these that hold up the whole spire, and it's got a bow in it, maybe by about 4 inches, which is slightly worrying. If I hit it, I can actually hear, it's a very high ringing sound, which means it's really stressed incredibly hard.
Since the spire was completed, it has had to have buttresses and bracing arches added to help support it. Up until the 1880s, tall building ambitions were restricted by the available material, stone and brick.
The tallest masonry building in Chicago was 16 stories tall, but the walls of that building by the time it came to the sidewalk were 6 feet thick. And so architects and engineers were realizing that, notwithstanding that fact that they had elevators, the materials were causing limitations.
Then a new material revolutionized civil engineering: steel. So why did the introduction of steel make such a difference? This is a 1 meter high pier of brick. Its strength can be demonstrated by how much it can be compressed. These hydraulic rams are slowly crushing the brick. At 45 tons of pressure, the bricks begin to fail. Minutes later, they have completely collapsed. This is a steel column, the same height as the brick. The column easily passes 45 tons with no signs of stress. As the compression increases, the peeling paintwork is the first indication of strain. But it's not until 90 tons of pressure is applied that the steel begins to buckle. So steel gives twice the strength of brick, and it does it for a quarter of the weight, which means there's much less stress on the structure. With the arrival of steel, the age of the true skyscraper could begin. In 1890, the city of New York had only 6 buildings more than 10 stories tall. By 1908, there were more than 500.
None of these buildings which you see out there would have been achievable if it wasn't because of the mass production of steel and its introduction to the construction industry.
The 20th century witnessed the rise of super tall towers. Steel was redefining man's horizons. But even the strongest steel can only take so much, as New Yorkers found out on September the 11th, 2001. Steel was the material that made the modern skyscraper possible, creating buildings that until the 20th century were just dreams. But with great height came new problems. The huge weight of a skyscraper is carried by the steel structure. It's vital that steel keeps its strength. A fire can spell disaster.
Once you heat the steel up beyond temperatures of sort of 550 to 600 degrees C, you're starting to see significant reductions in the load-bearing capacity of that steel.
So from the early 1900s, engineers began protecting the steel structure with fire-resistant coatings. But on September the 11th, 2001, how vulnerable steel still was became tragically apparent. Yet as the world looked on in horror, many engineers watching on TV believed the Twin Towers would stay up.
Like most structural engineers, I was watching live immediately the aftermath of the planes hitting the towers, watching it while the towers were still standing there and burning.
The first thing was the sheer shock at seeing what had happened, and initially thinking that, the buildings are going to survive.
I had absolutely no idea that these towers were going to collapse into a heap in the ground.
But collapse they did. The future of the skyscraper seemed to be in ruins. Construction on skyscrapers around the world ground to a halt.
People have become obsessed with what happened on September the 11th, and understandably so. It's such a traumatic and experience and a tragedy for everybody involved. But it's hardly as if it's the first time, and it won't be the last time, that a plane has hit a skyscraper.
The events of a summer's day in 1945 over the skies of New York are now seen in a new light.
People appear to have forgotten that a B-25 bomber hit the Empire State Building only a few years after it was built.
With visibility down almost to zero, traveling at 200 miles an hour, the bomber crashed with terrific impact into the 78th and 79th floors of the building, smashing through 7 walls.
When the Empire State Building was hit, if the aircraft had struck in a different place, maybe it's slightly higher or slightly lower, you would have seen a much more serious incident there. Potentially something as serious as happened on September the 11th.
The Empire State had a lucky escape, yet engineers heeded the warning. The new super skyscrapers of the 1960s, including the World Trade Center, were designed specifically to survive an impact from a passenger jet. So why did the Twin Towers fall down?
Where you actually hit the building and how the building is damaged in the first instance, in that first impact, does have a big variance on what the overall result is going to be.
The Twin Towers withstood the initial impact, but still collapsed. In the 2 years since, Simon Lay has studied what happened intensely.
There are a lot of misconceptions about what happened on September the 11th, and most of them tend to be simplifications over what happened. It's very easy to look at World Trade Centers and say, well, a plane hit them, that's why they fell over. Or it's very easy to look at them and say there was a fire in a tall building, that's why they fell down. And really, it's actually a combination of all these different factors.
Severe structural damage combined with a fire which was spread rapidly by burning aviation fuel proved too much for the Twin Towers. After 9/11, engineers are now using sophisticated new computer simulations to examine how fire attacks an entire steel structure.
We've effectively simulated either an aircraft impact, for example, or a bomb blast in this part of the building. So you can work out how heat actually penetrates that particular piece of structure, and then you can work out how long it's going to take before the structure gets hot enough to actually fall down.
Structural engineers are absorbing the lessons of September the 11th. They're designing skyscrapers to survive much longer by adding more of what's known as redundancy. It means building a structure to hold together even when part of it has been destroyed.
We've looked at making absolutely certain that the building will survive until the last person has got out of the building. We can't allow people living or working in these buildings to be so vulnerable to an event like September the 11th.
So the goal is to design a skyscraper to survive even when the unthinkable happens. In 100 years, skyscrapers have leapt from 10-storey brick to 100-storey steel. All of a skyscraper's weight is eventually transferred down to the ground. This ultimately takes the strain. The building of the modern skyscraper begins out of sight, deep below the earth. Today's skyscrapers can have foundations more than 100 feet deep, but the nature of the ground they rest upon is a crucial factor.
One of the unique aspects of New York, and especially Manhattan, is that the rock conditions of the city, which are fantastic to put up high-rise buildings.
But if the ground conditions can suddenly change, it doesn't matter how good the rock is. This is what happened in San Francisco in April 1906. A massive earthquake destroyed more than 25,000 buildings, including many of the city's first skyscrapers. Designers struggled for 70 years to engineer against earthquakes. Then, in the 1970s, they started using a technique called base isolation. This involves separating the building from the ground beneath it. The theory is that when the ground shakes, the building shouldn't. But some earthquakes are so severe that not even this is enough. Mexico City, September 1985. Extreme earthquakes devastate the capital. At least 18,000 people die, many of them inside buildings more than 10 stories high. This was a turning point in the seismic engineering of skyscrapers.
The engineering profession learned many painful lessons on that earthquake.
Earthquakes here are like nowhere else in the world.
The earthquakes in Mexico City are normally different from earthquakes in other areas like California or Kobe in Japan, where the earthquakes come with very strong accelerations and short pulses, and just a few short pulses. In Mexico City, we have a very long duration earthquakes with long shocks.
But engineers were determined that a repeat of 1985 had to be prevented. If they wanted to build skyscrapers, a new solution was needed.
So we thought that we needed a different way to dissipate the energy from the earthquake.
In 1993, Enrique teamed up with Ahmad Rahimian to design a unique skyscraper in Mexico City, one custom built to ride out the most extreme earthquake. Its name is Torre Mayor. Torre Mayor means tallest tower. Just cleaning the windows of this imposing structure takes courage. At nearly 740 feet, this is the highest building in the whole of Latin America. It's also one of the world's first intelligent buildings.
It has intelligence is embedded via the design into the buildings, and the building knows when there is an earthquake coming, how to respond to it in the most efficient way, and how to deal with the impulses and the energies that is coming to the building.
This is Torre Mayor's true genius. It has a unique design of crisscrossing interconnected shock absorbers called dampers.
The shock absorbers is similar to the muscles of the human body. In effect, the muscles are protecting the bones, the skeleton, the same way the shock absorber is protecting this structural framing, which is a skeleton of the building.
The dampers work by reacting to the energy of the earthquake.
What you see in my hand is a smaller version of the shock absorbers that is placed in the building. It's a simple rod which enclosed by a solid steel shaft. And as you're trying to press the rod into the cylinder, you have resistance. If I go several times fast back and forth, if you touch the cylinders, you would notice that it's getting warmer and warmer.
No detail of earthquake proofing has been overlooked. In this machine room, every piece of equipment has springs, buffers and seismic joints to ensure it remains operational after an earthquake. Torre Mayor's first big test came in January 2003. An earthquake measuring 7.5 on the Richter scale caused widespread panic in the city. Inside Torre Mayor, it was barely noticed. So skyscrapers that can adapt to dynamic ground conditions are the best measure against earthquakes. But what of the future of skyscrapers? Despite the shock of 9/11, buildings much taller than the Twin Towers are nearing completion.
Most of those projects which were being talked about before September 11th have now come back and are progressing because people are back up to speed on the idea. It's the practicalities, the economics of urban living dictate tall buildings, and therefore, we will continue to build tall buildings, and what we have to do is make sure we build them right and build them safe.
Skyscrapers are spreading across the globe. Soon the title of the world's tallest building will be taken by this massive structure in Taiwan. It's called Taipei 101, an astonishing 1,670 feet tall, nearly 200 feet higher than the Petronas Towers.
The skyscraper began in the US, but now the skyscraper is a global phenomenon.
But the big change is still to come.
We are going to make these buildings progressively more and more intelligent, so that you don't just have a fixed solution that sits there, but the building changes and adapts to what's going on around it.
The next level of technology is going to be 100 plus stories using active control systems. We're familiar with that technology in our cars for anti-lock brakes and traction control and things like that, but it's not familiar technology in buildings, but it will be soon.
The ultimate skyscraper is becoming a reality. From celebrity footballers to heads of state, the bulletproof car is today's ultimate status symbol. On the street, it's the first line of defense in an attack.
The best type of bulletproof vehicle would be one that is not noticeable to the passerby on the street.
Over the last 70 years, it's been modified and perfected with lessons learned, often the hard way.
Had the roof been armoured, I believe we would have all survived the assassination.
A masterpiece of engineering that can withstand armour-piercing bullets and direct bomb blasts, buying its passengers the time to get out of the kill zone.
Get out of the area. Avoid blockades. Avoid follow cars. Get out of the area as fast as you can.
But with every security advance come new threats. Designers are still grappling with the challenge to build the ultimate bulletproof car. This is a state-of-the-art bulletproof car. Its armour can resist handguns, assault rifles, and even armour-piercing rounds. The engine can be started remotely to protect from car bombs. It's the security vehicle of choice for passengers under threat.
Some of my clients I just prefer not to name. Most of them I prefer not to name. But I've had some pretty exciting clients, like Saddam Hussein, for example, from Iraq.
In this closed world, it's a game of cat and mouse between attacker and armourer, each second-guessing the other. With new security accessories that can now save lives, engineers are still striving to improve the armour and glass of the bulletproof car. Bulletproof cars have been saving lives for years, ever since politicians and criminals realised they needed protection. Al Capone's car of 1933 was state-of-the-art.
The glass on the windshield is 1 1/4 inches thick. On the doors, it is 1 inch thick.
But as weapons became more powerful, the bulletproof car had to change. And the first step is to create bulletproof armour to resist both ballistic and blast attack. There are 3 levels of armour protection, and they vary depending on the threat.
There's 3 categories of threats that are present around the world. The first category is handgun level protection. So here we focus in on the .44 Magnum, which is one of the most powerful handgun ammunition in the world. We have assault rifle protection. And then we have the armor-piercing levels of protection, which are fired out of the exact same weapons as the assault rifle ball ammunition, except here that the projectiles are now made out of hardened steel.
One of the largest armouring companies in the world is O'Gara, Hess and Eisenhart. They've been armouring cars for the past 50 years. In 1976, Kevin Claday started working here.
When I started, the cars were very heavy. Steel was heavy. We had installed the armor using hammers and anvils.
This heavy armour offered protection against the 3 levels of attack and still looked discreet on the car. But in the 1970s, cars began to change. They got smaller and lighter. Traditional armouring was no longer possible.
As time went on, the way the cars are built, they weren't able to hold as much weight, so we were facing a very big dilemma on how we could achieve armor-piercing protection in newer cars.
Engineers needed to find a lightweight alternative to steel. In the 1970s, they found the material they were looking for. It was called Kevlar and made from tightly woven man-made fibres. Richard Davis, a maverick inventor, pioneered Kevlar as a body armour and had a novel way of testing it too. Car companies took notice.
These are the Kevlar panels that we use when we're trying to get a high level of protection, especially from armor-piercing rounds. This came in very helpful in the mid-'80s when armor-piercing was beginning to be a real problem, and we had to go to lighter steels to keep the weight down in the vehicles.
With the introduction of Kevlar, armourers were able to achieve the same ballistic protection, but with much less weight.
What we were able to do with this is place this material behind the steel so that the steel would break up the bullet and the Kevlar would catch the bullet.
New materials solved the problem of weight, but designers were faced with a new challenge: how to connect all these materials together safely without leaving vulnerable areas. These vulnerable spots are called ballistic gaps.
You can shoot a sample and you can pass all day, but then you can take that same material and put it in a car, and if it's not integrated in the car correctly, then you can have failures and you can have ballistic gaps.
Ballistic gaps don't only let in bullets, they're also a weakness in bomb attacks. A ballistic gap would prove fatal in a bomb blast in Dublin in 1976, where Brian O'Driscoll was working as a driver for the British ambassador. On the morning of July the 21st, Brian was driving Sir Christopher Ewart Biggs from his Dublin residence. But the IRA had planted a bomb and was lying in wait.
It was a lovely sunny morning. At about 10:15 in the morning, we just left the residence, And 100 yards down the road, in this culvert, the IRA had planted 600 pounds of jelly knight.
The impact of this blast was horrific.
It blew a huge crater in the road. The car somersaulted in the air and came down on the roof on the passenger side.
While Brian was driving an armoured car, it had one failing.
It was a bulletproof car, very heavily armoured, but unfortunately the Achilles heel was that the roof wasn't armour plated. And when the explosion happened, the car somersaulted, they say up about 40 foot into the air, and landed on the passenger side on the roof, which collapsed.
Incredibly, Brian survived, but the terrorists were successful in killing 2 people, including their target, Sir Christopher Ewart Biggs.
The roof collapsing didn't give them any chance on the passenger side. Had the roof been armoured, I believe we would have all survived the assassination.
This was a very obvious ballistic gap, and from this point on, car roofs were armoured too. When Brian was ambushed, bomb attacks were not the norm, but times have changed.
There's a statistic that 60% of the attacks in the world are now bombings instead of direct fire. We decided to evaluate our current armor systems as they were against these types of threats, and we found out that they didn't perform very well at all.
Engineers went back to the drawing board to find out exactly what a blast does. With sophisticated welding, they created what they hoped would be a blast-proof vehicle by building a cage inside the body of the car.
A blast vehicle essentially is a welded cage that goes all the way around the inside of a vehicle to be able to take the blast wave and route it up and over and underneath the vehicle.
This sophisticated welding would be put to the test not long after in Kosovo. In 1998, John Sheehan was working as a diplomat and would rely on his car for his life.
I had the sensation that I was being hit by something that was causing me to accelerate upwards. It felt like I was taking off in a jet aircraft. I was fearful. I was afraid that I or one of us was injured or dead.
John had driven straight into an ambush.
We were driving down a hill. I heard a sound. It sounded like a loud clap. I thought we'd been hit by a rocket. I turned out I was wrong. We'd driven over an anti-tank mine.
Fortunately for John, he was driving an armoured car with the latest high-tech welding.
There is no doubt that if I had not been in an armoured vehicle, if I'd had a similar type of mine strike, I would have died.
To see one of your vehicles like Major Sheehan's having gone over a mine and see the destruction of the vehicle and hear that the people inside have actually walked away is very satisfying.
Defeating blast waves is a constant challenge. One development is being pioneered by British scientists who have a new idea that may be lighter and just as effective as a welded cage. Eric Chadwick is an inventor driven to defeat the force of the deadly blast wave.
So we're now putting the charge under the wheel.
Yeah, you've got 2 kilos.
This is what happens when an unarmoured vehicle is blasted with 2 kilos of TNT, equivalent to a moderate-sized landmine.
3, 2, 1, fire!
The blast wave has ripped the car to shreds, shattering the glass and resulting in certain death for any driver. But Eric thinks he's found the material to defeat blast waves. He's created a stone sponge that absorbs air pressure, and he's called it Tabor.
It's essentially made out of flint particles held together with a special resin. These flint particles are a peculiar shape, so it's got holes through it. So what we've effectively done is stuck a lot of little holes together, all the right shape and the right size, to take out the air pressure.
With the same amount of explosives, the Tabor reinforced vehicle is put to the test. But will it work?
3, 2, 1, fire!
British scientists think they've found the material to defeat a blast wave in a bomb attack. Here, they're about to test it with 2 kilos of TNT.
3, 2, 1, fire!
At first glance, the Tabor reinforced vehicle has performed only marginally better. But on closer inspection, the glass is still intact, and a marginal improvement could be crucial.
Yeah, it's taken out the door is shut to start with.
Yeah.
This seat is intact.
Yeah.
There is no...
Oh, look. Far better there.
Yeah, it hasn't blasted into the compartment, it's just bent it a bit.
Yeah. No, I think it's far more survivable than the last one.
Tabor is still new to the armouring scene, but it's now starting to be used on vehicles around the world. And as attackers become more sophisticated, bulletproof armour can now resist armour-piercing and even bomb attacks. Though technological leaps in armour have changed the bulletproof car in the last decade, it's in the area of glass that designers are now turning their attention to. Mexico. There are estimated to be thousands of kidnappings here every year. In the last 10 years, sales of bulletproof cars here have gone through the roof. But then, so have the number of weapons. In 1997, Mexican policeman Juan Russo would rely on his bulletproof car in a shootout. He'd survive, but he would lose many colleagues.
I'll show you where the first bullet landed. It was here, aimed directly at my head. Their bullets started landing here, all over the windscreen.
In an attempt to capture a Mexican drug trafficker, Russo and his team were ambushed.
We had presidential authorization to use the army. I went in my bulletproof car with 6 other patrol cars, Cherokee helicopters, motorbikes. We went to the agreed location, then the shooting started. When I got to the scene, they attacked us.
Little did the gangsters know, Russo's car was completely bulletproof.
Not for 1 second did they think I had a bulletproof car. They thought I had a normal car. When they saw that they couldn't defeat my tyres, windscreen or anything else, they focused on the people behind me. And thank God, I was able to drive away.
Despite huge casualties on both sides, Russo and the team succeeded in capturing the gangsters. Had it not been for his bulletproof glass, there's no way he would have survived. Bulletproof windows are made with normal glass, and the bullet is defeated by sheer mass. To make the glass tougher, you simply add more. Stopping the bullet was not the issue. In fact, this test shows that a .44 Magnum can be defeated by glass, only a few inches thick. The glass has stopped the bullet, but as this footage shows, shards of glass fly out the back of the bulletproof glass and into the car's interior. This is called spalling, and it tears the skin to shreds. In the 1970s, designers finally solved this by layering normal glass with sheets of plastic, each layer dissipating the bullet's energy. The magic was in the last layer, polycarbonate. This gives the windscreen an inner coating to catch shards or spalling that may fly inside the vehicle. To show how important this layer is, we will fire the same weapon at the same thickness of glass, but this time with the polycarbonate layer. The result? No penetration and no spalling. In this attack, the passengers would have escaped uninjured. No sooner had designers improved the glass, attackers moved in for the kill. It was the old enemy, the ballistic gap.
The first thing that the attacker shoots at is the glass. And what happens is they'll hit the center of the glass, and when they find that the bullets aren't going through, then they'll start hitting around the edges. And that's a weak point in an armored car. So what we do to protect against that is we put overlap armor, such as is in this window opening, and that'll overlap the glass and keep the edges of the glass from separating and having the projectile go inside the car.
While glass has traditionally been the Achilles heel of the bulletproof car, it has changed dramatically over the past 30 years, and plastics have transformed it for both drivers and attackers. With the best armour in the world and the most sophisticated glass, cars need to move quickly to get out of the kill zone. From run-flat tyres to smoke dispensers, the way they do this is with security accessories. Extras on an armoured car is not a new idea. Al Capone had a siren.
The siren in this car would enable Capone to get away at any time, as it is one of the laws in the United States that no one but an official, a police or a fireman may have one of these on his car.
And today, security accessories complement the armour of a bulletproof car.
These are the kind of accessories that you might find in a high-end armored vehicle. What we have here is a specially processed fuel tank that's foam-filled and has a special membrane on the outside of it. What this allows to happen is a bullet can penetrate the tank, and the foam will prevent the tank from exploding. The membrane on the outside of it will close over the hole that the bullet made and stop the gas from leaking outside the vehicle. This is a run-flat device that's installed on the drop center of a wheel, and a regular tire is inserted over the top of this. What the key is when the tire's shot out and the air is deflated, the tire is able to ride against the run flat and allow you to drive at 30 miles an hour for about 30 miles.
But extras don't end here. Ron Kimball has been building bulletproof cars since the 1970s. He sold cars all over Latin America and even to Saddam Hussein. But where Ron specialises is in security accessories.
I think the accessories have the magic that they really are designed to be a deterrent. They will not save one's life, but they will give you those extra 3 or 4 seconds that may save your life.
The way Ron started to devise bulletproof extras came from Hollywood. In the middle of a sales pitch, Ron's client asked him what sort of extras he could offer.
And then I thought James Bond, and I thought, you know, I can be as creative as the James Bond movies. So I started creating certain options in my mind, and 2 that came to mind initially were the electric shocking system. I wanted the vehicle to be, if you touched it, you would be shocked and not be able to get near the vehicle. And then I also wanted the smoke screen that comes out of the back of the vehicle.
But if Ron had the brainwave, it was his men back in the factory who would have to turn his fiction into reality.
When I came back from Europe with the idea, all I saw was shaking heads saying, no, it can't be done. And I kept saying, it has to be done.
It took months of attempts to come up with the right solution to make a smoke dispenser. The men tried different materials until they finally got it right. The answer was something found on any garage forecourt: antifreeze.
This is the container for the antifreeze, which creates the smoke. The pump inside, this is the pump, takes the antifreeze from the container, puts it down into the exhaust manifold or the exhaust pipe through a copper tube. That creates the smoke around through the back. Smoke comes out of the exhaust in this manner. Go ahead. And this is one of the most exciting things about this business, is that you can have options like this, save people's lives from the James Bond type technology.
In the event of a car chase, a smoke dispenser can come in very handy. But Ron's security accessories don't stop here. Ron had a plan to electrify the whole car.
Forgive me the pun, but it can be a shocking experience to be electrified through your fingertips.
After months of work, Ron's men figured out they couldn't electrify the whole car. but they could place an electric current in a wire behind each door handle. And it worked.
So we took the 12-volt battery system and created a converter. The converter converts 12 volts of electricity into 110 volts of electricity, and we've run that through wiring harnesses through the vehicle only to the doors, so that if anyone comes to the door, they would be shocked with 110 volts of electricity in each of the doors. And you can see that demonstrated by me with this tester. This sound and light, flashing light, indicates that there's 110 volts of electricity in each door handle.
With nuclear and chemical filters, security accessories are getting more sophisticated. 5 seconds after pressing a button in this vehicle, each of the 4 doors explodes, allowing a quick getaway. Security accessories are still changing the bulletproof car, making it harder for attackers to defeat. In the last 30 years, the bulletproof car has changed drastically, and designers are still striving to make these vehicles more like normal cars, so they blend in. But in the face of an attack, can a car ever really be bulletproof?
Nothing is bulletproof. If you can put enough shots and have enough time, you can get through it.
Based on the studies, the normal terrorist attack takes place in 7 to 15 seconds, meaning that you only have a few seconds to react. And in 15 seconds it's over with. You are either going to be gone or dead.
A bulletproof car isn't invincible, but what it gives you is something that may save your life: time.